So good morning, everyone. Good evening, depending where you are. I'm Valeria Luscri from area Lille, North Europe. I'm really glad to be the session chair for this session of IoTDI, Edge Computing, and that is composed of two papers. So the first speaker of the paper Rim of Floating Inference to the Edge is Itao Yu. He is a PhD student from University of Southern California. He's working on building an efficient deep learning inference system for edge and cloud computing. And today he will talk about how to schedule deep learning model in the edge cluster. You have 15 minutes. Please take your alarm on, and the floor is yours.
Oh, sorry, 15 minutes, 2%, not 20 plus 5, just 15?
It's 15 minutes and 5 for the question.
Okay, can I start? No? Okay.
Yes.
Hello everyone, my name is Itao Hu. Today I will to present our paper, Ring, Floating Inference to the Edge. This is a joint work with Wei Wu, Shelton, Raj, Ramesh, as well as Dongju and Wei Han for IBM. So nowadays, deep learning has revolutionized multiple fields, such as computer vision and speech recognition. Deep learning models have achieved state-of-the-art results for tasks like object detection and audio translations. So therefore, in order to leverage the benefit of deep learning, application developers are starting to use deep learning models to build media applications, which processes video or audio streams in real time. For example, the active detection is powered by deep learning models, which will derive active detections results, such as one person from one of the camera is holding a bag, while another person is working, etc. Another example is language translation, where the language translator will translate an audio from one language to another. So two people who speak different languages can communicate directly. So the language translation can be decoupled into 3 steps. Speech recognition to convert an audio to text, neural translation to translate text from one language to another, and speech synthesis to generate audio in another language. So each step can be implemented using one deep learning model. And we run language translator on 2 kinds of GPUs. IoTDI is a desktop GPU, while Jetson HGX is the most powerful mobile GPU we have. We want to see whether the language translator can run on this mobile GPU in real time. And we find that IoTDI only took 0.8 seconds to translate a 2-second sentence, while Jetson HGX took more than 4 seconds. This is telling us that such a huge latency makes it impossible to run the language translator on mobile in real time. Then consider offloading the computation to the cloud, which has much more capacity than mobile. However, the average response time from the popular cloud providers such as AWS or Google Cloud ranges from 60 to 75 milliseconds, which might be too large for real-time application. So instead, we argue that the edge cluster is a perfect match for it. Companies like AT&T are starting to deploy edge clusters in their cellular towers, which has enough power to process deep learning models and have small latency since the edge deployed in the cellular tower is physically closer to the user. So therefore, the client can offload the computation to the edge cluster. For example, assuming that the cluster has 2 GPU machines, and the application can be decoupled into 3 modules. The edge cluster will run the first module on one GPU machine and the rest 2 on the other GPU machine. The edge cluster should be able to serve multiple clients concurrently. For example, the GPU on the left will run a module A and B from one user and module 1 from another user, leading to the following challenges. First, how to share the resources to improve resource utilization? So given the relatively limited capacity of the edge, it's common to share the GPU machines across multiple clients. And there are several sharing strategies. Which one is the best fit for the edge workloads? Second, how to place models to guarantee low latency and high throughput. And there are lots of diversities in client requests, making the scatter space very large. Third, the workload is changing dynamically, and edge cluster only has limited capacity. So how to serve as many clients as possible is another challenge. Next, we will address these challenges one by one with the corresponding system design. First, how to share the same hardware across deep learning models. So there are two general ways to share the resources for high utilization. The first one is batching with time slicing, where the server system will combine multiple frames from different sources into a large batch, and then time slice hardware across batches. Batching is efficient when the batch size is large, so batching is widely applied in the cloud computing. However, when the batch size is small, batching will underutilize the GPU, leading to low utilization. For example, if it requires a batch of 4 to fully utilize the hardware, then a batch of only 2 will underutilize it. And batching within consecutive frames of the same source will also increase end-to-end latency significantly. So another way to share the resource for high utilization is spatial multiplexing, where we run multiple deep learning jobs concurrently on the same hardware. Spatial multiplexing is efficient even when batch size is small, so it is suitable for edge workloads where it's hard to form a large batch in a short span of time. But spatial multiplexing also brings up new challenges, since models on the same GPU will interfere with each other, which leads to our second challenge. Which models should be placed together on the same GPU? So namely, how to place models among the GPUs available in edge cluster. Before answering that question, we first need to dig deeper into our application structure. In Ring, each application can be represented by a media DAC. For example, the language translation application we mentioned earlier can be represented as an MDAC like this. And each module in MDAC can be implemented with one or multiple models. And different deep learning models have different resource requirements and accuracy. For example, the speech recognition module can be implemented by either Jasper or DeepSpeech-2. Module Jasper has higher accuracy with larger resource requirements, while DeepSpeech-2 has low accuracy, but also less resource requirements. We ran combinations for a given MDAC according to their accuracy and resource requirements. For example, it's clear that a combination of Jasper and Transform DIG should be more accurate and use more resources than a combination of DeepSpeech-2 and Transformer. We found that for each MDAC, a given worker can only maintain line rate to a certain rate, above which the output rate is no longer stable. For example, for a given MDAC, when the input rate is lower than 20, the worker can keep the line rate. But when the input rate is larger than 20, the output rate starts dropping. Namely, when the input rate reaches 20, the MDAC has reached the bottleneck. And we call this threshold the maximal frame rate. And in this case, it's 20. Based on this observation, we use the maximal frame rate to calculate the resource requirements. We assume an MDAC with frame rate of f will consume no more than f over capital F resource capacity. Let me give an example. Assuming we have two MDACs, worker 1 can sustain a maximal frame rate of 30 for MDAC 1 and 15 for MDAC 2. So now at the beginning, it has a rest capacity of 1. And due to GPU heterogeneity, worker 2's maximal frame rate is different from worker 1. And it also has a rest capacity of 1 at the beginning. Now we want to schedule MDAC 1 with frame rate of 20 and another MDAC 2 with frame rate of 10. Our system RIM uses a simple greedy heuristic for this bin packing problem. Details as follows. We first check whether we can place MDAC 1 on worker 1. Since the required capacity will be 20 over 30 according to our definition. MDAC 1 will place on worker 1, and we update the rest capacity of worker 1 accordingly. And we then try to allocate MDAC 2 and find that worker 1 doesn't have enough capacity left to serve it. Therefore, we try to allocate MDAC 2 on worker 2 and find that it is feasible. We then place index 2 on worker 2 and update worker 2's risk capacity accordingly. So note that in this example, we place the whole MDAC on one worker, which we call single worker placement. Namely, all modules in MDAC are placed on the same worker. And to leverage capacity efficiently, our system RIM also supports cross-worker placement, which will place modules from the same MDAC onto different workers. We also provide the maximum frame rate of each module on each worker, and RIM is using this information for cross-worker placement. For time limitation, I will skip cross-worker placement. For details, please reference the paper. In summary, RIM leverages offline profiling to place deep learning models. For example, it will first place one MDAC on worker 1, and place another MDAC on worker 2. And after placing these two MDACs, neither worker has enough capacity to serve any new MDACs. Then the third challenge arises: how to serve a third MDAC, namely how to accommodate more clients. Recall that each MDAC can have more than one instance. For example, the translation MDAC has two different instances, where a combination of Jasper and transform big is more accurate and uses more resources. So we borrow an idea from video quality adaptation. For video streaming, when the bandwidth is bad, the video resolution will be downgraded to guarantee user experience. And when the bandwidth is good, the video resolution will be upgraded. Therefore, in order to accommodate the third MDAC, we can demote MDAC 1 from Jasper and transform big to deep switch 2 and transformer. By doing so, we can save resources on the worker 1 to serve the third MDAC. And later, we can promote MDAC 1 back when MDAC 3 has finished. So in summary, for resource sharing, we need spatial multiplexing to increase resource utilization. And for model placement, we leverage offline profiling to place deep learning models. And we use promotion and demotion to serve more clients. Now let's talk about RIM's evaluation. We have RIM in an edge cluster containing 8 servers with a total of 11 heterogeneous GPUs, ranging from 10 Ti to Titan XP. We implement 4 different MDACs to deal with video or audio applications, and 3 of them have more than one MDAC instance to demote or promote. There are 2 systems closely related to RIM. Clipper is a service system that supports dynamic batching. It uses Kubernetes load balancer to direct requests, and does not support performance-aware model placement. Next supports dynamic batching as well. It is an internal load balancer to dispatch requests, and manage model placement and dynamic adapt to workloads based on the workloads. And we generate a few maximum workloads that RIM can support. And we measure the average finish rate for each MDAC, which is the ratio between output frame rate and input frame rate. We also measure the average GPU utilization from NVIDIA's profiler. A good inference system should have high finish rate with high GPU utilization. We run RIM, Nexus, and Clipper under 3 different workloads, and the result shows that both Clipper and Nexus has a lower finish rate than RIM for each workload. Specifically, Clipper's finish rate is 34 to 40% lower, and Nexus' finish rate is 10 to 28% lower. Which means that for these 2 systems, 10 to 40% of the requests either violates the latency SO or were never received. And to understand why this is happening, we show the finish rate for each client in the workload 1. We first analyze why Clipper failed. Clipper is able to achieve good finish rate for 8 of these clients. But for the rest 20 clients, the finish rate is low for 2 main reasons. First, Clipper does not do global memory management. So each container independently manages GPU memory, leading to memory contention. For example, client F9 raised out of memory error, leading to low finish rates. By contrast, RIM carefully deallocate memory after use, so it will never have memory issues. Second, Clipper does not do resource-aware placement, so it can place 2 relatively heavyweight clients on the same GPU. For example, client T9 run into resource contention, leading to low finish rates. And then we discuss why Nexus failed. Nexus achieved poor finish rate for traffic and phase change for 2 reasons. First, Nexus is focusing on GPU-intensive applications and only provides and schedules CPU module. However, chains like phase chain can be CPU intensive as well. So in our evaluation, next collocates all phase chain CPU module on the same machine. So all phase chain had a finish rate lower than 50. By contrast, RIM provides both GPU and CPU module, and you allocate 5 machines to run phase chain and achieve good finish rates. Second, let's use a latency splitting algorithm to derive each module's latency SO. But this algorithm implicitly assumes homogeneous GPUs in the edge cluster. But our testbed contains a range of GPUs, and we deliberately designed our testbed this way to mimic hardware heterogeneity resulting from incremental upgrades. And to run next in our testbed, we used the average latency profile as input to the latency splitting algorithm, which does not accurately reflect the latency on some of the GPUs, leading to low finish rate. And to evaluate the benefit of promotion and demotion, we compare RIM with RIM high and RIM low. RIM high will always use models with larger resource requirements and higher accuracy, while RIM low will do the opposite. The middle panel shows the workload, where we first add a new session every 10 seconds until we reach the full capacity of the edge cluster. Then we maintain the workload for 30 seconds and then remove a session one by one every 10 seconds. For the first 200 seconds, until the workload saturates the cluster, both RIM and RIM high have comparable finish rates. But at 200 seconds, a total of 19 seconds runs on the cluster. So when the 20th session arrives, RIM detects that it's running at full capacity and starts to demote MDAX to release resources for the new session. For example, at T200, RIM demotes session 1 to accommodate session 20. And at T equals to 220, instead of demoting session 3, which doesn't release enough resources for the new session, RIM demotes session 4 to accommodate session 22. And for the first 350 seconds, RIM keeps demoting sessions to accommodate more sessions and achieve nearly perfect finish rates. On the other hand, RIM high's finish rate drops beyond the 19th session because RIM high always uses the module with the largest resource requirements, therefore reaches the cluster capacity after the 19th session. So meanwhile, RIM low's utilization is lower than RIM because RIM low always uses modules with the lowest resource requirements, which didn't fully utilize the resources. So maybe I need to skip a few slides. And in summary, compared to RIM high and RIM low, RIM supports 80% more MDAX than RIM high, given the same amount of resources, and RIM utilizes resources more efficiently than RIM low. In conclusion, RIM uses MDAX profile to derive placements to satisfy latency and throughput requirements. It leverages performance and accuracy trade-offs to increase utilization and to limit more MDAX. Experiment results shows that competing approaches designed for latency SOs are not able to satisfy our requirements, while RIM can. And that's all.
Thanks a lot for your nice talk. Sorry, there was a mistake. It was 20 minutes actually. I recall that the session is recorded, and please, if you have any question, this is the moment. Is there any question? So I will start with some question. If anyone will have later, they can also ask later. First of all, I would ask you which could be a specific application that could benefit for this type of framework.
So your question is, what kind of applications can benefit from this kind of framework? Am I understanding correctly? Okay. So as I mentioned earlier, like for those media applications like active detection or like language translation, which has like strict latency SO to run the application in real time. So those applications might not be suitable to run either on mobile or in the cloud. So we can use our system deployed in the edge cluster, which has smaller latency, but also has enough capacity to process these workloads. So those applications with real-time latency SOs and also has large computations are suitable for our framework. That's my answer to your question.
Are you considering it is an open source framework that you are considering or not? Are you considering that aspect?
Yes, that's a good question. So now currently we are still trying to polish the code, and we are planning to release the code in the next few months. That's our current plan.
With the pre-license?
Yes, of course.
Okay.
Just release code like other system on GitHub, stuff like that.
Okay. Okay. Nice. And if you should characterize your contribution, the originality of your contribution in respect of existing framework, what you say, what it is different and original in respect of other existing framework?
Yes, one of the key difference between our work and previous work is we are focusing on the edge workload, which has like relatively sparse requests for each module. So it's very hard to form a very large batch like those one in the cloud. So we, instead of using batching only, we combine, we use like spatial multiplexing to run requests from different models on the same GPU concurrently. So that's another way alongside batching to further increase the utilization given the edge workloads. And besides, we try to like pick up the proper model variants to given the current resource available to accommodate more clients. That's also like another contribution to our paper. So this work is totally focused on the edge workloads. So that's why we designed the system slightly different from the previous system.
Okay, thanks for the answer. Any question from the? There is a question. Maybe you can also unmute your microphone and ask the question lively if you prefer, or I can.
I see a question. How do you upgrade downgrade them in that is already? Do you need to hot execution? Yes, I saw a question on the message. Yes. So the answer is no. I don't need to hot the execution. When I demote or downgrade or upgrade the model, it will be running in the background. So yes, that's two cases. If we are demoting the cases, we only need to aggregate some memory of the GPU. We still need to halt the current execution. And once the new models are ready, we can switch smoothly to the new models. So we don't need to halt the execution and restart in that. Instead, we can do everything smoothly, transparent to the user. That's my answer to your question.
Any other question?
Yeah, any more question, you can send me email or anything, I guess.
Okay, so thanks Itao for your nice and interesting talk, and we can continue with the next speaker. The next speaker is Sumuk Marate. I hope I pronounced it well, the name. Is a research fellow working at Microsoft Research India under the supervision of Professor Ashkai Nambi. He will try with the live presentation, and he will present the paper Current Sense, a novel approach for fault and drift detection in environmental IoT sensors. So the floor is yours.
Hey, thank you, Valerie. Yeah, just setting up the screen. Okay, is my screen visible?
Yeah.
Yeah, okay, good. Yeah, hi everyone, and thank you for being here. I am Sumit Marathe, and today I'll be presenting Current Sense, a novel approach for fault and drift detection in environmental IoT sensors. This work has been done at Microsoft Research India in collaboration with Aspira Systems. Today, billions of IoT devices are deployed around the world to sense and monitor the environment. This increase in demand has led to innovation on the sensing side of things and has given rise to low-cost and compact environmental IoT sensors. These sensors are now making dense city-wide deployments a reality and is helping cities collect critical environmental data at a very high granularity. In a typical IoT setting, data is collected from multiple sensors and is then aggregated and analyzed to draw meaningful insights. However, the reliability of this entire pipeline is weakened by not knowing whether each sensor is working well or not. Since most of the sensors continue to send some garbage data even in failure, the presence of bad sensors in a dense deployment can have a catastrophic impact on upstream processes. This fact, coupled with high failure rate of low-cost sensors, leads to a lack of trust in the data from such dense deployments. Air pollution monitoring is a vertical where low-cost sensors are commonly used. As we all know, air pollution is a severe concern, and WHO estimates that more than 7 million deaths occur every year due to direct or indirect impact of polluted air. Sorry, my screen had frozen, so I couldn't see what's happening. I just kept on talking. To identify potential sources and curb pollution levels, it is necessary to have access to fine-grained data of the pollutant PM2.5. Introduction of low-cost air pollution sensors addresses this need and has paved the way to large-scale and fine-grained air pollution monitoring. There are multiple efforts from private companies and academia which experiment with collaborative sensing using such low-cost sensors. However, almost all such efforts report a high rate of sensor failure. This is CPS-30, a $50 PM sensor manufactured by Sensirion. Like the rest of the PM sensors, this sensor also works on the principle of light scattering. What happens is there is a laser diode and a fan inside the sensor. The fan controls the airflow, allowing particles to pass through a beam of light, which is emitted by an LED. Light is scattered by the particles and is then detected by a photodiode and converted into particle count and mass concentration values. One of our key observations over here is that a majority of the data faults encountered in such PM sensors can be mapped to a failure or degradation of the hardware components in the sensor, such as the fan and the laser diode. To understand the impact of a damaged sensor component, we conducted a controlled experiment. In this figure, we can see PM data of two co-located sensors plotted over time. In the first 60 minutes, both sensors have a working fan component in them, and we can see that data from both are in agreement. However, at the 60-minute mark, the fan component of sensor 32 is replaced with a faulty fan. Immediately, we see that data from the two co-located sensors start to disagree. Even in disagreement, however, the data from both sensors look valid and are free of any anomalies. Thus, the only way such a fan fault would be detected would be via a co-location method, and that is a cumbersome effort. Similarly, in the figure to the right, we conducted a similar experiment where at the 80-minute mark, we replaced the LED of sensor 33 with a faulty one. We can see that the data from both sensors are in agreement till the 80-minute mark, but start to diverge afterwards. This experiment thus highlights that component failures can lead to severe data faults which can go unnoticed if only the sensor data is observed. Similarly, to understand the impact a drifted sensor component can have on PM data, we conducted another experiment. A PM sensor labeled sensor 9 was deployed in real-world settings for a period of 44 days. We first co-located a high-end reference monitor with sensor 9 on day 1 for a period of 5 hours and plotted the data over time. We can see that the data from both are in agreement. On the last day of the deployment, that is on day 44, we again co-located the high-end reference monitor with sensor 9 for a period of 5 hours and plotted the data. However, this time there is a slight deviation in the two data streams, which implies that there's a data fault. Upon analyzing sensor 9 in lab after the deployment, we identified that the fan component in the sensor had drifted and the fan speed was changed. Thus, due to this difference in the performance of the fan, the PM data reported by the sensor on day 44 was showing errors. As the growth in drift in sensor is dependent on multiple factors, component drift can lead to significant but unpredictable data errors over a period of time. Presently, data-centric solutions are commonly used to identify faulty sensors. A common data-centric method learns distribution of data using historical data and data from neighboring nodes. It then uses this learned distribution to identify anomalies in the sensor data. What these methods then do is that they assume that a high density of anomalies from a particular node implies sensor failure. Another assumption made by these methods is that a sensor failure necessarily gives rise to a data anomaly. However, based on some real-world deployments that we conducted, we observed that this is not necessarily the case. In this figure, data from two co-located sensors is plotted over time. Even though both sensor 17 and 15 show similar anomalous behavior with certain spikes in PM data, sensor 17 is actually working while only sensor 15 has a fault. This goes on to show that a data anomaly does not necessarily imply a sensor fault. The figure to the right again shows PM 2.5 data from two co-located sensors. It might seem that both the sensors are working perfectly, as data from both looks meaningful and free of anomalies. However, based on the ground truth information, we know that sensor 11 has a fault in it and only sensor 7 is working. Thus, the assumption that a sensor fault implies a data anomaly doesn't hold true. From this, we can see that an ideal approach for sensor fault detection probably should not rely on non-stationary environmental data, which can show hyperlocal variations. So this leads to our key research question that we try to answer. How can we detect sensor data faults that are caused by failure or drifts in the component of a sensor without using data generated by the sensor? And this is where our approach comes in. Our approach, called current sense, uses the current drawn by the sensor to our approach, called current sense, uses the current drawn by the sensor to derive unique features that differ between working and faulty sensors. The key intuition behind this approach is the assumption that a faulty sensor would show some change in the physical and electrical characteristics and would thus give rise to differences in the current drawn. For example, in this figure, we can see the current draw of a working sensor is quite distinct from as that compared to of a faulty sensor. The current sense approach has three key characteristics. The first characteristic is that it can identify component-level sensor failures. In the figure, we can see the current draw of a working PM sensor. When the LED in the PM sensor is switched on, the current draw of the sensor increases. Since the switching on and off of the LED in the sensor is controlled by a set algorithm, we can see a highly repeatable current signature. Now, if there were a fault in the fan component of the sensor, the current draw would change and would look like the waveform in orange. Similarly, if the LED in the sensor goes bad, then the current draw of the sensor would again change and look like the waveform in green, and the peaks which corresponded to the LED on state would be distinctively missing from this waveform. And last but not the least, if there is a failure in both fan and LED, the current draw would look like the waveform in red, with lesser amplitude and no peaks. Thus, due to this significant difference in the current draw, current sense is able to identify the faulty components in a sensor. The second characteristic is that current sense can detect and quantify drifts in the components of a sensor. We can see that the current profile of a sensor with LED drift shown in orange has lesser amplitude as compared to that of a working sensor. Similarly, the current profile shown in green is of a sensor with a drifted fan, and we can see that it deviates from the profile of a working sensor. Thus, this shows that current sense can detect and also quantify drifts present in the sensor. The third characteristic of current sense is that it is independent of the measured phenomena, which is concentration of PM 2.5 in the case of PM sensors. This is one of the most important characteristics as it makes current sense robust to changes in the environmental factors. In the figure, we can see current draw of two working PM sensors deployed in two extremely different environments. Sensor 17 is deployed in a location where the PM2.5 concentration is artificially raised to around 200 microgram per meter cube, and the temperature too is raised to 55 degrees Celsius. Sensor 20, on the other hand, is deployed in a location where PM2.5 concentration is relatively very low, around 10 microgram per meter cube, and the temperature too has relatively low value of 15 degrees Celsius. Even in such extremely differing conditions, we can see that the current draw waveform of both sensors remains nearly identical. Thus, current sense differs from the rest of the fault detection approaches, as the environment has no or minimal effect on its efficacy. The three characteristics of current sense can be used to build a robust pipeline for fault and drift detection. The first component of this pipeline would be measuring current draw. The second would be fault detection using the measured current. And the third would be drift detection using the measured current. We'll start with the current measurement component of the system. Most IoT devices deployed today have a battery monitoring circuit which is capable of measuring current. While the current draw of an entire IoT node would be an aggregation of all peripherals in the device, if the MCU is able to power down energy-consuming peripherals like radios, a clean current sense waveform can be captured. The figure to the right gives an example of this, with the waveform in orange, the one where the peripherals, high energy consuming peripherals, are switched off. Thus, if an IoT node has an inbuilt battery monitoring circuit present, no extra hardware modifications are needed for using the current sense approach. However, if the current sense device does not have an inbuilt current measurement capability, what we have done is we have fabricated a small add-on PCB which can be fitted to the sensor. This board would measure current drawn by the sensor and would transmit it over UART or I2C to the IoT node. Thus, using minimal hardware add-ons, we can then enable current sense on any IoT node. The second component in the pipeline is fault detection. Based on the sensor datasheet, the LED and the fan components of PM sensor operate at two different frequencies. Thus, to characterize the behavior of the LED, which operates at 0.4 Hz, we sample the current at 30 Hz. Similarly, in the case of fan, as it rotates at a speed of about 300 Hz, we sample it at 5 kHz to get a clean current draw waveform that can characterize the fan's behavior. Now, to derive robust features from these current waveforms, we calculate the fast Fourier transform of each time domain signal. By combining these 264-point FFTs of LED and fan signals, we compute the 128-point feature vector that is used by a classification algorithm. The classifier is basically a decision tree model. For training this model, we collect feature vectors of both working and faulty sensors. For this purpose, we collect 100,000 fingerprints, each from 5 different sensors, which includes a working sensor and a sensor from each category of fault. Note that the entire data collection process is conducted in the lab environment and takes just a few minutes to be completed. We then collect a testing data set, which is comprised of 100 signatures each from 7 different sensors, which comprise of working and faulty sensors, and which were not part of the training phase. On this testing data, our trained model identifies faults with a F1 score of 99%. This trained fault classifier now can be used for fault detection in a real-world deployment. Now we come to the last component of the pipeline, which is drift detection and quantization. When a fan in the PM sensor starts to drift, its RPM starts to vary. If you observe the current draw of a fan, which is rotating at 15,000 RPM, and compare it with the current draw of a fan, which is rotating at 7,000 RPM, we can see that both the frequency and amplitude of the waveform decreases with decrease in RPM. A similar change in amplitude can be observed when we measure the current draw of a sensor with fans rotating at 3,500 RPM. If we plot the relation between the frequency of current draw of the waveform and the fan RPM, we can see that there is a perfect linear fit. Thus, it is evident that a drift in the fan component creates a proportional frequency drift in the current draw waveform. Now, if we take a look at the other side of things, drift in the fan RPM intuitively causes a drift in the airflow in the sensor. Due to this change in airflow, an error in PM data is generated as the PM sensor assumes a fixed amount of airflow. If we combine these two mappings, we can actually calculate the mapping between drift in current sense waveform and the PM error. Thus, using current sense, we can detect drifts in the fan component and also quantify it. A similar behavior is also observed for the LED component. As the light intensity of the LED starts reducing, the current drawn by the LED starts dropping. The plot to the right shows a relation in between the LED intensity and the magnitude of the dominant frequency component of the current waveform. We can see that there is a good linear fit present in between the two. Now again, on the other side, with decrease in LED intensity, the PM data starts to show errors. These errors are also directly proportional to the amount of drift in the LED intensity. If we combine these two mappings, we can again calculate the relation in between drift in current sense waveform and increase in PM error. Thus, using current sense, we can detect drifts in the LED component and also quantify it. All the three components of the system come together to label the sensor as working, faulty, or drifted. First component, current drawn by the sensor is measured and passed on to the fault detection algorithm. The trained model is then used to classify the sensor into fault and no fault scenarios. If there is a fault in either the fan or the LED component, the process is halted and the sensor is labeled as faulty. However, if there is no fault, the collected current signature is then passed on to the drift detection and quantization process. What this process does is it computes the component operating characteristics like the RPM or the LED intensity from the current draw and then compares it with the values observed at factory settings. If there is a difference between the two, the sensor is labeled as drifted and the drift is quantified in percentage PM error and is given as an output. However, if there is no drift present, the sensor is then labeled as a working sensor. Thus, with this evaluation pipeline, a sensor is classified into working, faulty, and drifted categories using the current sense approach. To evaluate our proposed system, we conducted a real-world deployment. By partnering up with Respara Systems, we conducted an 8-month-long deployment of 51 PMS-7003 sensors in the Bengaluru urban area. For collecting the ground truth, we used a handheld and high-end reference monitor, which we used to co-locate with every sensor under test on a weekly basis. Based on the data observed during co-location, we attached the ground truth labels of working, faulty, or drifted. The results of the real-world deployment are as follows. Out of the 51 sensors deployed, 18 sensors developed some data fault by the end of the 8-month time period. That accounts to 35% of the deployed sensors. We evaluated performance of a data-centric method and a current sense method for fault detection on 17,340 samples that were collected in the period of 8 months. The data-centric method, due to the issues highlighted previously, gave a low FN score of 67.2%. On the other hand, the current sense-based fault detection approach gave FN scores in the range of 97 to 99% for each classification category. Thus, this shows that current sense is a robust approach for sensor fault detection, as even though the training data was collected in a lab setting in a few minutes, it does a better job in fault detection compared to the data-centric approach, which is actually trained on long-term real-world environmental data. Another thing to note is that along with sensor faults, our system was also able to identify all 9 drifted sensors that were present at the end of the 8-month deployment. This plot shows the drifted sensors in red and highlights that the drift in PM data was identified by the drift observed in the current sense waveforms. We also went a step ahead and tried to compensate or correct the data faults caused by the sensor drifts. By taking percentage PM error, which was reported by a system, we tried to correct or remove the PM data error using an upstream process. In all 9 drifted sensors, the average RMS error before applying any correction was 16.76%. Applying the simple drift compensation technique brought the average RMS error down to just 2.88%. Thus, by using drift compensation method, a huge 86% reduction in average PM data errors was observed. This verified that not only could current sense identify fault and quantify drifts, but with the right mapping, it can also correct data errors caused due to drift in the PM sensors. While we primarily conducted the study and evaluation of current sense on PM sensors, we also evaluated the scalability of the approach to other environmental sensors. For example, in this plot, data from 2 CO2 sensors is plotted over time. One of the sensors has a fault and the other one is working. However, the data from the faulty sensor is not distinguishable from the data of the working sensor. For a temperature sensor, the plot to the right shows data from a working and a faulty sensor. However, again, it is evident that data from a working sensor is nearly identical to that of the faulty sensor. Current sense again can give a robust fault detection performance in this scenario. We can see that the current profile of a faulty CO2 and a faulty temperature sensor significantly differ from their working counterparts, thus making fault identification a straightforward process using current sense. This study shows that current sense is indeed a generalizable approach and can be applied to a wide variety of IoT sensors. Thus, to conclude, in this work, we propose a novel sensor fingerprinting approach called current sense, which uses the current drawn by the sensor to identify sensor faults and sensor drifts. We conduct an 8-month-long real-world deployment with 51 air pollution monitors to verify if a proposed approach works as expected in real-world scenarios. We also go a step further and use current sense to correct and compensate data faults that are caused by drifts in the PM sensor. And last but not the least, we showcase that current sense approach is generalizable and scalable to other IoT sensors. That is all from my side, and thank you for your time.
Thank you, Sung, for your nice talk. Is there any question? So there is a question from Taimur. Is asking, can you read? Is asking, does proposed solution increase or decrease data size?
Yeah, so the proposed solution would, along with the sensor data, at a user-defined frequency, it would send the sensor status to the respective cloud service. So it would add some amount of bytes at a user-defined interval. But to answer your question in more detail, just to clarify, the computation of the sensor status is done on the IoT node side. So in terms of communication of the current sense entire waveform, that's not happening over any network channel, but it's computed on the node itself, and just the sensor status, which would be of just 1 byte true or false, would be transmitted to the cloud service along with the sensor data.
Okay. Any other question?
I had a question.
Please.
Thank you for the great talk. So on the slide, current sense characteristic 2, I think.
Sorry, do you want me to go to the characteristic 2?
Yes, I had a confusion about the block.
Yeah, just a minute. Fortunately, yeah, just a minute. Okay, here you are.
Yeah, over here, why there was like a circle around the third part. So why are we basically comparing the two drifts together? Why aren't we comparing it with the working sensor?
Yeah, so the blue one is the working sensor over here, right? But it's just overlaid by the orange one. So it's actually comparing with the blue one, but the orange one also has a working fan in it. So technically the part that I'm highlighting is the green one has a faulty fan. And over there, you can see the amplitude at that high frequency signal is lower, and the frequency is lower too, as we saw in the later slides. And the working sensor and the laser drift sensor, since both of them have a working fan in them, the characteristic of the high frequency signal is mapping to a working one. Does that answer your question?
Yeah, it does. Thank you.
Yeah.
Any other question? I would have a question regarding the data. Which type of data you used in for assessing the performance of your framework? It was real data or also synthetic data?
So just a minute, I'll just go to the real deployment slide. So let's see which one. Yeah. So we conducted this real world deployment of 8 months, right? So we had 51 monitors deployed, and so the entire evaluation is conducted on this real world data and not synthetic data.
It was only based on real data. And to achieve a reasonable accuracy, which is the amount of data you need?
Right. So if you are referring to the training part, yeah, sorry for this jumping around. Yeah. So for the training, what we did was the evaluation on the of this project is basically done on real world sensors. But for the training of the supervised model, what we did was our partner provided us with these working and faulty sensors, right? And we just collected the signatures of these sensors in the lab environment, and it just took like probably 20 to 30 minutes to collect about 5,000 to 6,000 fingerprints from these bunch of sensors. So that formed our training set and testing set for controlled in-lab experiments.
Okay.
Which was later followed by the real-world deployments of the 51 monitors that I mentioned.
Okay.
Excuse me, can you hear me?
Yes, we can hear you.
I am Temur. It was a great talk. It's a great presentation. So I have another question, if you would like to answer. Like your solution, I guess, works on the based on the current measurements, and I'm curious that if data sets are already collected, how does this solution can help us to clean data drifts which on the data sets which have been collected already, like if how we can extend this work to already collected data sets if we are not interested in new data sets or new deployments in real world, but we have data sets already, and we just want to remove the drifts from that data and remove abnormalities, and what are your insights on this one?
Right. That's a good question. So to first answer your question, so that the entire fault detection mechanism is based on the availability of this new data modality of current signatures, right? So to apply this method on any current any existing data set of sensor data, right, what we would need is in at least in some form the current drawn by that IoT node when the data was sent, right? And then we can run our basically feed that current signatures to our trained model, and it can give you the sensor status at that particular point of time. So does that answer your question? And in terms of in terms of future deployments while collecting data sets, what the suggestion would be, like, if you want to use this current sense approach, you have to have some current measurement circuitry there inside the IoT node, which logs the current data. So that's one thing. And again, like, sorry.
Thank you very much. Great presentation. Good luck.
Yeah, no problem. Yeah.
I believe there was another question from Ashkay Nambi. Is asking, the retrofit does not require any change in the sensor design. No, this is the, sorry. If the sensor doesn't have the current sense inherently, would retrofitting require board modification? And I believe Ashkay Nambi already answered to that, but I don't know if you can read and want to add something.
Yeah, so the question was like, if there is already a current measurement circuitry in the node, do you need to add an additional one? Was that a question?
Yeah, I can take that.
Yes,
so the question was, if the sensor doesn't have a current sense inherently, would retrofitting require a board modification, right? So as I mentioned, the board does require a retrofitting of current sense, but we have designed a simple PCB, right, which goes on top of the sensor. In that way, you don't have to change any sensor design, as shown here. Yeah.
Got it. Thanks.
There is another question. Can you read it, or do you prefer I read it? For same sensor type, but from different manufacturer, should it train different fault detection models separately? I think you already...
Yeah. That's a good question. What I'll do is I'll just stop my screen, just change the screen sharing type and go back to the slide deck, because I just have a single monitor and it's slightly getting inconvenient. Yeah. Okay, so actually I have a backup slide for that, luckily. So the question was, yeah. So due to the paucity of time, I didn't highlight this characteristic. Adding to the three characteristics, there is another characteristic that the current signature would remain the same for different units of the same type of sensor, while it would change for when the sensor type is changed. So for example, you can see over here for two PMS-700 sensors, the current waveform is exactly the same. In the graph, you can see five waveforms from 5 different sensors. And in the plot to the right, you can see current signatures of a plant or sensor and a Sensorion sensor. And you can see that due to changes in the internal algorithms running on these sensors, you can see that there's a difference in the way these the both of the sensors draw current. But to take it a bit, take it a level further, in terms of if you have a deployment which uses just one type of sensor, all you need to do is collect the data for that from one sensor, and it can be extrapolated to all the other units of that particular type.
Okay.
Does that answer your question? I didn't catch who was asking it.
Yes, thank you.
Yeah.
He said
Yeah.
yes, thank you.
Okay.
Okay. Any other question? We have just a couple of minutes. So it seems that there are not any other question. I would just thanks again the speaker for their talk, and good evening or good morning to everyone. This is the last paper of the session, so this will conclude the session number for IoTDI. Thank you, everyone. Have a good day.
Hello, everyone. We'll just wait for a few minutes for people to join in, and we'll kickstart the session. Thank you. Right, let's get started. By the way, the session is being recording for your information. Okay, let's get started. So, hello everyone, welcome to the 5th session of the IoTDI. I'm Akshay Nambi. I'm a senior researcher at Microsoft Research. I'm glad to be the chair for this session titled Human in the Loop. This session has 2 papers. The first one is titled Deep SQL, Understanding Sensor Data via Question Answering. And the second paper is titled Fair IoT, Fairness Aware Human in the Loop RL for harnessing human variability in personalized IoT. I request the attendees to post the question or comments in the chat window, and after the talk, I'll pick that up to ask the presenter. And each presenter gets 20 minutes of time for the slides and 5 minutes for Q&A. To present the first paper, I invite Tianwei. He obtained his PhD from UCLA this year. His research mainly focused on deep learning sensing and time series data modeling. He's currently working as a researcher at Samsung Research America. Tianwei, all yours.
Yes, thanks for the introduction. Hello, everyone. I'm Tianwei from UCLA. And here I'm going to present our work called Deep SQL, which understands sensor data through a question and answering approach. And this is a collaborative work funded by the DICE ITA project. So let's start out by looking at our motivation first. Recently, there's this explosion of mobile, wearable, and IoT devices, which generate a huge amount of the data and enable different kinds of sensing applications. And on the other hand, with huge amount of data accessible, the data-driven method is developing fast. And we use machine learning, or especially the deep learning techniques on a wide range of applications, like the visual understanding, machine translation, speech recognition. And also demonstrating the excellent performance on various sensing tasks, the deep learning models are usually trained to perform some fixed tasks. And the existing pipeline of training the deep sensing model is like this. With a given task, we collect the corresponding data set, and then we train the model. And the inference they make are usually limited to a predefined set of high-level labels. But with a set of sensing devices, users need to perform various sensing tasks. And when a new task is introduced, we need to collect a new data set, do the labeling, and train a new model again. And this pipeline is pretty clumsy and time-consuming. And it also greatly limits the application scenario of the deep learning sensing. So here, to make this system more flexible during the inference time, we want to know if it's possible to have some generalized model that not only understands the sensory data, but also perform reasoning according to users' different requirements. Well, the answer is yes. We know that the complex tasks are usually composed of some atomic events, and these events are shared across different tasks. For example, the footstep counting requires the detection of walking activities and also the footsteps. And in some other applications, like the workout tracking task, those atomic events are also monitored and processed. So with the given specification of the task, we envision a model that can create the corresponding reasoning module automatically during the inference stage. So here, we take inspiration from the natural language processing domain, where there are active research on tasks like the text question answering, the visual question answering, and database question answering. This system allows the user to question about the context data, like the images, the text, and also the tables. And then the system could answer those questions accordingly. And this QA system can take the open-ended question in the form of natural language. So we believe that this restricted form of such a capability should be possible for the spatial temporal sensory data as well. And we can imagine in the future that a human decision maker is not really limited to a fixed set of inferences computed from the sensory data, but he could instead ask flexible questions about the event and the activities in natural language form. For example, a user can interact with the smart devices by asking questions like, how long did I exercise between lunch and dinner yesterday? And how many times did I drink water yesterday? Also, instead of looking at the traffic events, and the statistics collected from the traffic sensor, a city manager could ask questions such as, how long did the congestion on the freeway 99 last? And was there an accident during the hour preceding the events? So in this vision, the task requirements are provided at runtime by the non-expert user as the questions in natural language form. And here, our interested questions can be the activity of the user, the status of the house, or maybe the events across the city. And our context here is a multitude of sensory data. So based on these, we would like to propose this task of sensory question answering, or we call it SQA. And we would like to mention that actually the question answering is more important for sensory data, because the sensory data collected from the sensors like the IMU, the barometer, and also even the radar are just a series of physical values. And humans usually have a hard time associating those values with a high-level symbolic concept. So basically, we couldn't really characterize these physical phenomena, and we cannot understand them directly because we don't have the appropriate vocabulary describing those events. And the system SQA here actually helps the user to understand the sensory data better. So in this work, we introduce a SQA system which should satisfy these three requirements. Firstly, it should answer questions from different perspectives. For example, given the raw IMU data, the system needs to answer questions that not constrained to a specific format, but can be of different types. Like it can answer the binary questions, like did the user do something, or the counting questions, how many times and how long did the user do something, or some open-ended query questions, like what did the user do after doing something like that. And secondly, the SQA system should answer the complex compositional questions, which means that we can combine different reasoning steps together and build the compositional questions of larger complexity. For example, we can ask, how long did the user exercise after lunch and before dinner? And thirdly, this SQA system should generalize to the new complex questions. Since the questions are compositional, which means that the question space can be large or sometimes infinite. And as a result, the questions being asked at the training time will not overlap with the testing questions. So instead of memorizing each individual questions, this SQA system should learn to understand what's the meaning of each activities and also their temporal relationships, the logical steps. And then the system should know how to use them to understand the new questions. However, before going into the SQA system, we are still facing a huge gap where the dataset for the SQA task is not available yet. To train the system satisfying all our needs, this dataset needs to have the complex questions that involves the notion of both space and time, and also their dependencies. And the question and context in the dataset should be of large scale. And also the question need to be compositional and can be arbitrarily complex. So as the first step, we propose an automatic tool for the SQA dataset generation, or we call it SQA Gen. This tool uses this template-based approach to generate the questions. And we can always augment this tool by adding new question templates to support different application needs. And to automate this process, all the data here, the sensory data, the questions and answers are all accompanied by the associated semantic representations. Specifically, the sensory context use a thing list to represent its semantics. The thing list as here is a sequence of different activities, where each activity is a tuple consisting of the activity type, activity duration, and also the starting time. And with the natural language questions, we use a functional program to represent it. For example, the question here, what did the user do before opening the fridge and after closing the drawer, can be represented as a functional program below. The query action type specifies the type of the question, and it has two temporal relationship operations. the relate before and the relate after, connected by this logical operator AND. We have implemented all these atomic programs and stored them in the function catalog. And we apply the functional program on the thing list, and we can get the ground truth result of the questions, which can be then converted to the natural language form. So this figure here shows the data generation pipeline of this SQAGen. And we start with some underlying labeled sensory data. It would be great if the data is untrimmed to keep the transition natural. And then we can split the raw data into sequences based on our requirement. And then we create the semantic thing list representation. We randomly sample the question template from our question base and apply those function program on the thing list to get the answer. And I'd like to mention that in addition to using a big number of natural language templates for question generation, we also perform a grammar correction and a synonym change to make sure that questions are natural and have linguistic variations. The final generated dataset has all these three parts: the raw sensory data, the natural language questions, and also the natural language answers. So in this work, we create the dataset called OpQA on sensory question answering about the human activities. Here we use the opportunity dataset as our source dataset because this dataset have the raw IMU data collected from the distributed wearable sensors. And it's also well annotated with different level or different hierarchies of activities. And it also unsplitted raw sequences. Our generated OpQA dataset different question types, like the action query, action comparison, number comparison, existence, and counting. And after generating the questions, we also balance the question type and balance the global answer distribution to reduce data biases. And finally, the generated dataset has around 1 million unique questions and 1.3 thousand unique sensory contexts. And here I list some of the examples for the generated questions of different types, like the existing question, the counting, action query, time query, action comparison, and number comparison, with also the possible answers. And based on this data set, we propose a generalized SQA framework. Basically, this framework is composed of three parts. And based on different input modality, the sensory processing module extract informative features from the distributed sensory context and then fuse them together into the sensory representation. The question processing module process the natural language questions to get the question representation. And then the final SQA module combines this information together, perform the required reasoning on the sensory information, and then predict the best answer. Within this framework, we implemented several SQA models. This figure here shows the architecture of our proposed model called the deep SQA based on the compositional attention mechanism. And in this model, for the question processing part, instead of using this pre-trained embedding method, like the word-to-vec was a global vec method, we instead use a learning embedding matrix to get a word level representation. This actually shows better performance than the pre-trained method. And then we use a two-layer bidirectional LSTM model to get the question level representation. And for the sensory processing part, we use a convolutional LSTM model to process the raw IMU data and get the sensory representation. And the SQA module here uses a series of MAC cells based on the compositional attention mechanism to iteratively perform the reasoning on the context data. And finally, we use this softmax activation to predict the best answer within a high frequency answer set, which is obtained during the training data set. And in our evaluation, we implemented a set of baselines for the performance comparison. And these baselines are mostly adopted from the VQA task, but modified to process the sensory data. The prior and the prior Q are the basic statistical method. They choose the most frequent answer as predictions based on all the questions or based on each of the question types. And the convolutional LSTM model is a question blind model, which only takes the sensory data as an input, guesses the questions, and then predicts the answer. And the next one, LSTM model, on the contrary, is a context blind model, which predicts the answer based only on the questions. And finally, the neural symbolic method uses the pre-trained perception model that is natively trained on the opportunity dataset to get the inference of atomic events. And then it uses hard-coded reasoning function to perform a set of tasks, dependent reasoning to get the answer. So the reasoning logic here is 100% correct. Also within this deep SQL framework, we implemented 3 different networks using using the stack attention network, the convolutional LSTM model, and also this compositional attention network we just illustrated. For the general performance, we can see that the prior and prior Q method shows good performance. And in the prior method, the accuracy of the binary question is a little above 50%. And in the prior Q method, the accuracy on the action query is around 4%, which proves that the dataset has really small biases. And the neural symbolic method here also shows poor performance. And we believe this is because the perception model that works on the opportunity dataset is not strong enough. It only gets around 70 to 80% of accuracy. And the error in the perception stage would accumulate in the reasoning part and would finally affect the result of the question answering. And finally, the proposed deep SQL model using this compositional attention mechanism achieves the best performance for all different question categories. We also performed some experiments analyzing the system performance with respect to the task complexity. For the figure on the left, we analyze the performance with number of reasoning steps in the query. Basically, we can see a decreasing accuracy with the increased number of logical operations. For the question with 7 reasoning steps, some models here have even a performance boost. And we think this is because that in our dataset, the number of questions of this category is larger, so the model tends to answer the questions better. And for figures on the right, we generate a 4 variance dataset with 500, 750, 1000, and 15,000 time steps in the time window. And with the window length increasing, clearly the performance of our model decreases. So the sensory context here is a crucial factor affecting the SQL task complexity. And finally, we test the generalizability of the SQL system. Here we split the dataset into the testing set. We split the testing set into these 2 parts: the test familiar and test novel. The test novel here has different queries from the training dataset. So all the testing questions are new. And from this table, we can see the proposed model have a small accuracy drop, but basically within the basically maintain their performance. So we think the SQL model learns to recognize the tokens and perform the basic logical operations, and then predict the answer based on the composition of logics, instead of just memorizing the semantics of each specific training questions. We also noticed that the gap of the SQA compositional attention is actually smaller than other competitors, meaning that this proposed model is more robust to the new questions. And one of the future direction of this SQA is that we want to make it neural symbolic. Right now, the system is a pure deep learning model and is trained in an end-to-end fashion, and the prediction is not explainable. And the major drawback here is that this pure data-driven approach is data intensive during training and also memory consuming to store the learned dependencies. And based on our evaluation, we also see that the model performance decreases when facing longer sequences, like the complex question programs or longer sensory time window. So here we'd like to introduce this idea of neurosymbolic system to SQA, where we can have the perception model converting things and question into their semantic representation. And then based on the question programs, the reasoning model can be constructed during the runtime and applied to the structured things. And using this compact symbolic representation, this envisioned system can be more efficient and robust to the complex scenarios. And to summarize, in this work, we introduced the deep SQA framework, which generalized the QA framework to address the SQA problem on the raw sensory data. And in addition to the deep SQA, we create this SQA Gen framework for generating the SQA dataset by using the labeled sensory data. And we also generate the OpQA for benchmarking different SQA models. We evaluate those models across the state-of-the-art QA models and lay the foundation of challenges. We also provide the open source implementation of all the framework, the dataset tools, and the access to the generated dataset to help facilitate the future research. And thanks for listening to the presentation. And I'm looking forward to your comments and questions. Yeah.
Well, thank you for the nice presentation. Audience, do we have any questions for TM? Okay, I can start with the first question while people start putting in. Okay, wait, there is a first question. Let's go with that. The question is, what's the length of the time window you're using in SQA, and how complex could the task be in time window of such length?
Well, thanks for asking. Right now, we test a bunch of different lengths for the time window, as we mentioned in the experiment result slide. Basically, the time window ranges from 500 time steps to 1800 time steps. And for the opportunity set with this sampling rate of 30 Hertz, the maximum window is around 1 minute. And actually, this size is large enough for the time series data, considering that most of the existing applications only focus on events happening in a few seconds. And also for this data set, we have an average of more than 10 activities happening inside the window. So it's not hard to compose the complex questions asking about the temporal relationship between the events.
Right. And the second question was how complex it will be as you increase the length of the time window.
Yeah, I mean, from our observation, we can see that when we are increasing the time window, the performance would drop gradually. So basically, the length of time window is a key factor for this the task complexity. And we right now we assume that maybe when facing some more complex task in terms of both the question complexity and the time window length, maybe we should like turn to the a neurosymbolic method instead of just this end-to-end approach.
Right. And the next question was, does the QA generation tool apply to other data sets as well?
Well, of course, this tool is actually designed for this generating the SQL data set using the labeled time series sensory data. So it needs to take a source data set that is labeled, of course, and it's better to be unsplitted data. And the reason here to use the unsplitted data here is to keep the transition between the activities natural, instead of just concatenating different sequences together to introduce this artificial noise. And also for different application scenarios, we can easily augment this tool by adding new question families, which is the semantics of the new questions. And then we can add the new question templates, which is the natural language representation of the questions, to create more tasks and to increase linguistic diversity.
Right. And the follow-up question which I have, right, is how does the current framework handle noisy sensor data and also even noisy annotations, right? How does your system handle that?
For the noisy annotations, right now we don't really like take that as an issue, because we assume that the data should have like the ground truth annotation for the underlying sort of sensor data. And also, I think you mentioned some the other noise in the dataset.
Yeah, the inherent noise in the raw dataset.
Another factor that we're considering is about the questions we generated, if they are like natural enough, and if they should be like evaluated by the real humans. Like we use some crowdsourced method to evaluate how real this question can be, and in that direction.
Right. Does anyone else have any other questions? We have time for one final question. Let me ask that. So you mentioned that the question, the SQA, right, needs to answer from different perspectives, right? Could you briefly talk about how do you train the network, right, to provide answers from different perspectives?
So are you suggesting that the answer from different perspectives? Well, okay, right now, I mean, the SQA can handle a question from different perspectives. It means that it could handle the questions of different dimensions. Like you can ask questions about, ask either binary questions or like open-ended questions. You can ask about the temporal relationships, or maybe ask about the query about specific event, or maybe counting. It's just like a different combination of the logic operators.
Right, got it.
And the system to handle those different questions, the system basically need to learn the function of each of the specific operator instead of learning the semantics of a single question.
Okay.
And then it learns to combine them together to cope with the new questions.
Okay, thank you. Let's thank the speaker. So we'll go on to the second paper in this session, which is called Fair IoT. And I invite Salma El-Maki, who is an assistant professor in the Department of Electrical Engineering and Computer Science at the University of California, Irvine, where she leads the Pervasive Autonomy Group. Salma, take it over.
Thank you for the introduction. Can you allow me to share?
Yes, you should have the permission.
So, yeah, okay, let me share my screen. So I'm going to play a pre-recorded video for my presentation. Please let me know if the voice is not clear, okay?
Hello, everyone. My name is Salma Al-Malaki. I'm an assistant professor at UCI. Today, I'm going to talk about the fairness for human-in-the-loop IoT system and how to address the challenges of human variabilities. So first, let's ask, what is personalized IoT? So with sensors becoming pervasive and are equipped in every aspect of our daily life, there are enormous amount of data that are streaming from multiple IoT devices. These amount of data can actually help us understand the environment around us and adapt to it autonomously, even learn how to react to scenarios that we haven't seen before. In the heart of IoT system is the idea of building cognition on the environment in order to take an appropriate action. However, IoT systems have to be adaptive, and the most important kind of adaptation is the human adaptation. By adding the perception of the human in the loop of computation, we are actually adding a new computational layer for the IoT system, creating this kind of cognition perception cycle where human reactions, behavior, intent are observed and coupled into the loop of computation. Human-in-the-loop systems are actually being adopted in many areas, including health, wellness, and medical systems. These systems are interacting more with humans, and they need to adapt to the human preference, behavior, and reaction. So this computation loop the perception cognition cycle that we talked about, starts from the physical sensors in embedded IoT systems that acquires the raw information about the current environment. Then this data is used to do further analysis and infer a higher level state, which can further be used to do an adaptation action based on some kind of a state action policy. This action is then fed back to the environment, and this loop continues. And in this talk, I'm going to focus actually on the adaptation part of the computation cycle that you're seeing here, especially when we want to adapt to an environment where human is interacting with the IoT systems. So adaptation in human in the loop systems faces a lot of challenges that actually arise from the fact that humans have intrinsic variability in their preference, in their behavior, and in their reaction. So we categorize these variability into three main categories. The first one is called intra-human variability, where the idea is that human can change their behavior over time. Okay, so hence you can't have some kind of a fixed human model. The second kind of variability that we identify is the interhuman variability. So because of this variability, you can't have one model that fits all, because every human has their preference and their change in behavior. The third kind of variability is the multi-human variability, where it becomes even more complicated when you want to adapt to multiple humans that are sharing the same application space. So the question will arise of which human you want to adapt to. And of course, this will naturally pose the question of fairness and equity. So usually, this interaction between human and environment is composed of two parts. If we want to model this kind of interaction, usually it is composed of two parts. You can have like deep neural network, a DNN, that performs the context inference and fusion over the data that you are observing from the environment. And then you can have a decision-making agent that takes this context and decides which action to take next. This is usually done through imitation or behavioral learning, which of course requires a lot of data. Now, as we are adapting to the human reaction actually needs to be learned to tune this policy. Hence, we need this notion of a feedback reward from the human environment interaction to keep on monitoring the human reaction to whatever action that is taken by the agent. So this fits nicely into the reinforcement learning paradigm. So in the standard reinforcement learning framework, a learning agent actually interacts with a Markov decision process over a series of time steps. And at each time step, the agent takes an action in its current state and receives a reward in the same time step. And through this kind of state action interaction, the agent's decision-making process tries to refine its policy to apply the action that is going to give it the best or the highest reward. So there are some underlying assumption in this model, the vanilla RL model. The first one is that it assumes time invariant rewards. It assumes that the actions that it's being applied impact the environment immediately. And it assumes that the rewards that you are receiving is actually corresponds to the corresponding action that you took at the exact time step. So, however, because we are dealing with human, we face these three challenges. That the first one, you have actually dynamic and time varying rewards because human may react differently to the same action over time because of the intra-human variability that we talked about. The second one is that human may ignore the actions if they are in the form of a recommendation. And the third challenge is that the reward that you observe should be calculated over a time horizon in order to capture the human response, because humans does not react to the change in the environment immediately. So in our previous work, we actually targeted these three challenges and proposed multi-sample RL that divides the time horizon into three overlapping different time scales. The first one is the observing rate TS, where the state of the environment is observed every time the new sensor data is available. And of course, this depends on the sampling rate of the sensors at the edge devices. The second one is the activation rate, TA, which is the time by which the agent should take an action. And the third one is the evaluation rate, TL, or the learning rate, where the reward should be evaluated at a relatively slow rate to take into account the delay in the environment and also the human response time. So we proved that by carefully designing the reward function, that multi-sample RL can actually handle the intra-human variability by keep on monitoring the human response and account for the dynamic and time varying rewards. However, response time of humans are different, and the rate of their change in behavior is different as well. Hence, there are two sampling or two time scales, the TL and the TA, should be adaptive. Accordingly, we need to adapt the TL and the TA assumed by the multi-sample RL algorithm. In particular, we propose Governor RL, which models the search over the best TL and TA for each human as a Markov decision process to learn the best TL and TA that enhance the human experience based on the rate of changes in their behavior and the changes in their response time. So by doing that, by combining multi-sample RL with Governor RL, we can actually address the intra and the inter-human variability. Now, the question is, how can we actually address the multi-human variability? So this is more challenging because when multiple humans interact in the same IoT application space, their preferences differ based on the number of people they interact with and the type of this interaction. Moreover, when the application adapts to one human, the environment changes accordingly to this adaptation action, and thus it can has a direct effect on other humans in the same environment. So in addition to that as well, that multiple humans may require different adaptation actions based on their different preferences. Hence, we need some kind of a mediator to intervene and manages these different and multiple adaptation actions from multiple humans to achieve some kind of an aggregate better experience for all the humans collectively that are sharing the same application space. So in particular, we want a mediator that observes the environment current state and propagate back the state to the multi-sample RL for each human, which in turn issues the appropriate adaptation action based on the learned policy for this particular human. The mediator then should take all these actions and apply one action to the shared environment, and then propagate the rewards that it receives from the environment based on this taken action back to the multi-sample RL in order to tune its policy. Moreover, since the evaluation rate or the TL that we talked about captures the environment's response time and the human response time, it should not change even while mediating multiple humans. However, the activation rate, the TA, should be mediated because it controls how often we apply an action to the environment. So the mediator should mediate two values, the TA, which is the action taken by the governor RL, as well as the actions taken by the multi-sample RL in order to affect the environment or apply one action to the environment in which multiple humans share the same application space. So the question will be how to design the mediator. So first, the mediator should choose the smallest value of TA because this will ensure the fastest activation rate across all humans. So this is the first thing. The second thing is that as for the actions that are proposed by the multi-sample RL per human, we cannot just choose one action from the list of actions. Hence, one idea is to actually use a weighted average of all the actions. So in principle, the idea of weighted average takes into account the varying degrees of importance of these actions. However, we actually don't know a priori which action is more important than others to achieve like a better cumulative experience for all the humans. Hence, we cannot just fix these weights. And as humans' preferences and moods and reactions are changing, one action may actually have more weight at a particular time while having less weight at another time. Hence, we need to learn these weights and continuously adapt them based on all the humans that are interacting in the same environment. So we need the mediator to be designed as an RL agent that adjusts the action's weights and then applies the weighted average action to the environment. And then the mediator RL will observe the effect of these weights by collecting the reward as a cumulative reward from all the humans' experience in the environment. Now, because the mediator RL will try to maximize the total reward by choosing different weights for different adaptation actions learned for multiple humans' preference. In one extreme, the mediator RL may actually end up favoring one adaptation action over the others by assigning high weight to it. This means that the mediator actually favors one human preference over the others because it looks at the cumulative performance. So how can we ensure fairness? So this problem, it's called the Matteo effect of accumulated advantage in sociology. And in other words, this phenomena where the rich gets richer and the poor gets poorer, and it actually appears because the mediator can actually assign more weight to a particular human preference because this human increase the cumulative reward. So one idea to actually mitigate the Matteo effect is to model the action taken by the mediator dictated by its assigned weight as a resource. And we want to ensure a fair share of this resource. So in this work, our definition of fairness is the ability to provide the same utility to all the humans, regardless of their relative effect on the overall performance of the system. So we define the utility of each human adaptation at time step as UHT. So in particular, UHT is the average weight assigned by the mediator RL for a particular human H over a time horizon from 0 to T, where the factor that you see here, J over T, is used to give more value to the recent weights learned by the mediator over the ones in the past. We then measure the fairness of the mediator using the coefficient of variation. So we are using the coefficient of variation of the human utilities as a measure of the dispersion of the probability distribution that captures the utilities received by each human. And the idea is that we want to minimize this dispersion. So the mediator is set to be fair, more fair, if and only if we are able to show that the coefficient of variation that you're seeing here is getting small. So based on this idea, we are going to ensure fairness in our mediator by adding a regulator to our reward function. So this regulator will capture the changes in the coefficient of variations, and we define a fairness scale since the performance of the system or the cumulative performance of the system and the fairness measure can actually be two contradicting objectives. So we add this fairness scale to give like an up how much we care about fairness versus the performance of the system. With this, we completed the fair IoT architecture that can actually handle the intra, and the multi-human variabilities. So these three layers of reinforcement learning agents, the multi-sample RL, the governor RL, and the mediator RL. And we can ensure fairness when we have multiple human shares in the same application space by adding this fairness regulator. Now, for the evaluation, we evaluated fair IoT on two human-in-the-loop IoT systems in the domain of smart house, where we focus on adapting the thermal system of the house. And the other one is in the domain of ADAS, where we focus on adapting forward collision warning. And in this talk, I will focus on the first application to show the results of Fair IoT. So as an introduction to this application, a human in the loop thermal system inside a house should take the human state and preference into the computation loop while calculating, for example, the heater set point. So for example, the human body temperature decreases when the human goes to sleep versus the human body temperature increases when the human exercise. The human stress and anxiety can increase body temperature. So we want to adapt the thermostat set point based on the human that is interacting in this thermal house. So to test the adaptability performance of the Fair IoT, we simulated the behavior of 3 humans as follows. As you can see here, we have 9 different activities with different patterns, and we simulate 3 human occupants, and we collect the change in their predicted mean vote, or PMV, across time, where PMV is usually used to measure the thermal sensation of a human as a scale between -3 and 3, where -3 means cold and 3 means hot. And the acceptable range of the PMV is usually between -1 and 1. And then we model the human as a heat flow that depends on the average exhale breath and the respiratory minute volume that are highly dependent on the human activity. The house is modeled by its thermodynamics properties, and then we designed Fair IoT to control the thermostat set point of this house. So as we described, governor RL, the state of its Markov decision process is a tuple, the TL and the TA. This state is passed to the multi-sample RL as a parameter. The thermal sensation, the behavior, and the state of the human are unknown a priori to the algorithm. So different TL and TA may give actually better thermal comfort for different human because of this inter-human variability. The state of the Markov decision process in the multi-sample RL, of course, depends on the human activity and the current indoor temperature. And the multi-sample RL will then choose the best set point to control the house thermostat based on the learned policy so far. The reward then returns back from the multi-sample RL as a function of the PMV, which in turn is used to calculate the total performance of the current TA and the TL chosen by the governor RL. And the performance is actually calculated based on 2 parameters: the moving average of the absolute value of the PMV score over the 5 days of simulation that we used. And the second one is the moving standard deviation of the PMV score, which is used to account for high fluctuation in the thermal sensation. Then the performance value that we use, it depends on weighted sum of these 2 parameters. Here we show the results of how governor RL with multi-sample RL can actually address the intra and the interhuman variability. First, in order to understand the results, we first fixed TL and TA and ran multi-sample RL for all combination of TL and TA to get some kind of a ground truth of which values will give the highest reward. Then we run multi-sample with governor RL, and as you can see, that governor RL actually converges to TL equal 10 and TA equal 10, which was the second best choice for human 1, as you can see here. We did the same thing for human 2, and as you can see here, that the best TL and TA are different from human 1 due to this interhuman variability. And you can see here that governor RL was actually able to converge to the best choice for TL and TA that gives the maximum reward for human 2. So these results actually show that governor RL is able to address the interhuman variability by converging to different TL and TA for different humans. Now, for the multi-human variabilities, where multiple humans share the same house, we apply the mediator RL to tune the weights of the adaptation actions coming from these 3 humans in order to apply only 1 set point to the house thermostat. So here, first, we are showing the results where we don't have any fairness regulator. We fix the values for the weights and tries all the combination of weights and see which combination actually gives the highest cumulative reward. Then we run the mediator RL without the fairness regulator. And as you can see here, that the mediator RL was able actually to converge to the weights that gives the highest reward. However, if you look at the coefficient of variations, you can see that it is increasing, which means that this is not a fair adaptation. This can also be observed by looking at the weights that the mediator chose, which gives highest preference or highest weight to human 3 most of the time. Then we run again with fairness regulator, and you can see here that the mediator actually didn't converge to a certain weight, but thanks to this kind of a fairness regulator that we have in our reward function, the mediator chose several weight combination across time and not necessarily the one that gives the highest cumulative reward. Now, if you look at the coefficient of variation, it's getting smaller, which is an indication that it is a fair adaptation. So with this, I conclude. In this work, we address the challenges in adapting human-in-the-loop systems to different human variabilities, including intra, inter, and multi-human variabilities, while addressing the fairness of adaptation for multiple human interacting in an IoT application. We propose fair IoT that has 3 different layers of RL agents interacting together that are designed to address these variabilities. And at the end, I want to share some last thoughts about fairness in RL. So RL algorithms in general enjoy strong mathematical guarantees regarding their convergence to the optimal policy. However, the mathematical guarantees for its fairness are still lacking. There have been some studies in the literature that actually extend RL algorithms to fair RL. And one example is to, for example, constrain the exploration strategy to avoid going into biased situation. Also, another thought is that the way that we define fairness and equity may change how we design the adaptation engines in RL. So indeed, the relation between the optimality of the policy and the fairness of the policy is an interesting area to explore. And with this, I end. Thank you for listening. Hello, everyone.
Thank you, Salma, for the great presentation.
Thank you. Open my video.
Yes, you're audible. Yeah. Do we have questions for Salma? Please raise your hand if you have a question or type it on the chat. I can pick that up. While people are typing or getting the question, the first question which I want to ask, right, Salma, is what was the data set you used to train the RL, right? Could we talk more about that?
The dataset. So we tried 2 applications, the thermal house and the ADAS. So in the thermal house, we use the thermodynamic model of the house to synthesize data, how the indoor temperature changes. And let me share my screen to show you the model that we use. So we synthesize data actually based on how we model the house and how we model the human. So let me share my screen. Share my slides. Here it is. Okay. Yeah. So in order to generate the data, we model the human as a heat source that depends on the way that they exhale and the respiratory minute volume. And these 2 parameters actually are very correlated to these activities. So based on an activity, we calculate the EPT and the RMV, and this will release certain kind of amount of heat from the human that will affect the environment temperature. As for the house, we model the thermodynamic of the house that depends on the wall insulation, the heat transfer, how the thermostat is changing. So based on this model, we can actually estimate the indoor temperature based on this model. And this is used actually in the state of the multi-sample RL, which is the activity and the indoor temperature. So we actually synthesize data through building this simulator.
Right. Okay. And when we, so this is simulated data, right? So when we talk about real world data, there you would have physical sensors, right? Monitoring the temperature and stuff. And these data could have noises and some uncertainties, right? Can you talk about how the RL framework would adjust to these kind of uncertainties?
Yes, so one thing is actually how can we get this thermal comfort, right? So we are saying that we are using this scale or this way to measure the thermal comfort, the PMV. It is a standard way to measure the thermal comfort. And there is a way, actually, there is an edge device that can be used to give you an estimation of the thermal comfort. It's called the black globe thermometer. So in the real world, the black globe thermometer will be employed in the room or in the house, and it will give an estimation of the latent heat temperature, which is going to be used to estimate the PMV, okay, of a particular human. As for the noise, the fact that the RL is keep on monitoring the environment, it's not just learning a fixed policy and that's it. But because we keep on monitoring the environment because of these changes that we talked about the human, even if there is some noise, it will fade away over time, right? Because you keep on learning, you keep on getting the data from the environment. It's not just collecting some data and fix the policy and that's it.
Right. Okay. We have another question. How is the fairness accomplished for different payment?
For different, sorry?
For different payment.
Payment?
Is that right, Anshu Narman? If you could ask the question.
The chat. I can't see the question in the chat. Can you repeat it again?
The question is, how is the fairness accomplished for different payments?
Different payments?
Yeah.
You mean the cost?
Yeah, the cost. Yeah, I think yes.
Okay, okay. Okay. So in this simulation that you're seeing here, it is a single house with multiple human in the same space. Okay, so they are in the same environment, in the same house, so the cost is the same. However, the question will be very actually interesting if you are looking at the adaptation when you have different houses. Okay, and each house is responsible for paying the cost of the amount of energy that they are using to adapt the thermostat. Okay, in this case, you have to include the cost also as another regulator in your word function. But in this case, the way that we simulated, the 3 people is actually are located in the same house.
Right. Okay. Thank you. Any other questions for Salma? Okay, so if you don't have any questions, I would like to thank all the speakers and thank all the attendees for attending this session. With that, I'll conclude this session and thank you for attending the session. Take care.
Thank you.
Hello, the next section starts at 1 p.m. we have a break for 15 minutes, and the next session will start at 1 p.m. and it will be about the edge computing part 2.
I don't think you can see the messages when I share.
Hello, welcome everyone. Good afternoon, good evening, and good early morning to some of you. So welcome to the afternoon session of Edge Computing Part 2. In this session, we have 3 presentations. I would like to remind the presenter that each talk will be allowed 15 minutes for the presentation and 5 minutes for questioning. So generally, I will not try to stop you from presentation, but if you are going over time, I will give you a verbal reminder. All right, so let's start the first paper. So Jiho Zhao, can you please share your screen?
Yes, please let me know if there's something wrong with the voice. 1 second.
Okay, go ahead. So I would just like to quickly introduce the presenter, Jiho Zhao. I think I hear some echo. Hello?
Hi, so can I start now?
Let me introduce you first. Okay. Can you mute your audio? Okay. Jiho Zhao just finished his master's degree at Duke University, and he will join IoT lab at the Chinese University of Hong Kong as a PhD student this summer. His advisor is Professor Guo Liangxin, and his research interests are efficient processing of deep learning and Internet of Things. So Jiho, please go ahead.
Hi, I'm Jiho Zhao from Duke University. I'm going to present this work RGML format for real-time deployment of apps. This work is during my internship at the Chinese University of Hong Kong. And let's
Sorry for the interruption.
University with the collaboration of Taiwan, Neiwen and Professor Guo Liangxin. So in recent years,
your voice is
algorithms
not very
are
clear.
increasingly adopted by a wide range of Internet of Things applications, such as autonomous driving and mobile augmented reality.
Can you pause?
Yeah, make sure when you do screen sharing, you select the share computer audio option.
Oh, sorry. Actually, I chose the share sound.
Hi, I'm Jiho Zhao from Duke University. I'm going to present this work RGML format for real-time deployment of apps. This work
So can you maybe just present the slides?
Oh,
I think your recording has some problem with audio.
okay.
The audio quality is pretty bad.
From Duke University. I'm gonna present it. Hi, I'm Jiho Zhao from Duke University. I'm gonna present this work, EdgeML, an AutoML framework for real-time deep learning on the edge. This work is during my internship at the Chinese University of Hong Kong and a master study at Duke University with a collaboration with Kai Wang, Neiwen, and Professor Guo Liangxin. So in recent years, deep learning algorithms are increasingly adopted by a wide range of Internet of Things applications, such as autonomous driving and mobile augmented reality. These applications often require sophisticated processing of large amount of sensor data within critical time constraints, which motivates the emerging trend of applying deep neural network algorithms on the edge and IoT devices. So in practice, State-of-the-art DNN models incur significant compute overhead, which imposes barrier for deploying them on the resource-limited edge and IoT platforms. Moreover, several applications are mission-critical in nature and hence must maintain a high level of model inference accuracy. As you can see the slide here, two of the main approaches have been proposed to address these challenges. Model compression aims at accelerating the execution of the DNN model locally. For example, pruning, which accelerates the model execution via reducing the neural processing. Similarly, filter pruning for reducing convolutional calculation. In addition to these techniques focused on optimization of local DNN execution, several approaches are proposed to accelerate the inference through collaboration between edge and cloud. So here it shows a very basic structure of deep learning inference with the help of edge computing. The initial image here, you can see the cat, is directly transmitted to the server for inference. After processing, the result will be sent back to the end user. We find that this pipeline may bring the problem of high latency because of the overhead of compressing and the transmission of the image, which is unacceptable for some time-critical tasks, especially when tasks are deployed on some resource-limited devices such as mobile phones. Where one of the potential solutions is DNN partition. Part of DNN compute workload can be offloaded to the edge cloud. Specifically, we can find a partition point in the CNN, maybe after the second layer of the network, and the computation before this point will be processed on the local device, while the rest of the computation will be on the edge cloud, which means the local device will transmit the middle feature matrix to the edge cloud. One representative previous work is neurosurgeon, shows in this slide. Undoubtedly, this is a very clever idea. However, this kind of approach faces several major challenges when being applied in real-world applications. One of the main issues here is how to make the decision of where to partition the model. Actually, a neurosurgeon provides us a way to iteratively search the best partition point in order to minimize the latency or energy consumption. However, a more realistic problem is that the bandwidth of the network is varying all the time. The bandwidth fluctuation can make the workload offloading strategy suboptimal, especially when it varies sharply. As you can see in this slide, to meet the system performance requirements such as end-to-end latency, the optimal partition strategy is changing all the time. So talking about model compression, a representative previous work that aims to deploy DNN models in IoT scenario is DDNN by Harvard University. This kind of work can be divided into progressive neural network. One or multiple side branches are inserted in the mainstream of the initial network, such that different input data can exit at different branches during DNN inference, leading to reduced computer workload. This kind of approaches also face several major challenges when being applied in real-world applications. For example, these approaches usually require careful consideration of model architecture as well as optimization of a large set of model parameters, such as compression level. In another word, in the case shown here, how many and what blocks should be inserted in the side branches. Additionally, the changes of data characteristics, for example, switching from bright scene to dark scene for an image object detector, will cause dynamic end-to-end delays in the progressive neural architecture, since the inference path may exit at different branches. In order to maintain a desirable trade-off between high-level model accuracy and bounded inference latency in the presence of runtime dynamics, such optimization decisions must be made in an online manner. So AutoML is an emerging framework that aims to automate the pipeline of DNN design. So one of the representative examples of applying AutoML is AMC, which applies AutoML to automatically compress DNN models. Similar to several existing AutoML solutions, EdgeML also adopts reinforcement learning for automated decision-making. However, instead of offline training, EdgeML applies the principle of AutoML to dynamically optimize the model execution policy online under the edge computing structure. So here we propose EdgeML. AgML integrates model prediction and progressive neural architecture, which allows to explore the optimal model execution policy that consists of branch thresholds in execution control of progressive neural architecture and the model prediction point in computer workload offloading mechanism. The execution of AgML system contains two stages. In the offline stage, the DN model is transformed in the progressive neural architecture and trained locally. Firstly, a branched model is constructed by inserting several branches across the layers of the original DN model. Each branch is further fine-tuned on the cloud to increase accuracy. Afterwards, a series of model prediction options are formed by selecting the prediction points at the granularity of the neural network layers to support the fine-grained layer-level workload offloading. The branched model and the model prediction points are synchronized between the edge and the cloud. The model execution policy, which consists of the model prediction points and the threshold for each branch, will be generated at runtime to determine how the DN model processes the input data. So in the online stage, AgML adopts an AutoML framework to update the model execution policy dynamically via the cooperation between the edge and the cloud. Due to the huge solution space for model execution policy and the dynamic environmental conditions, AgML adopts a reinforcement learning algorithm to search for the optimal execution policy at runtime. Each execution policy consists of a prediction point, threshold at each branch, and the policy update interval. The new execution policy is generated based on the measured performance of the previous execution policies from the edge, including the task latency, model execution accuracy, edge energy consumption, and edge cloud data transmission rate. So the left part in this slide here illustrates the model prediction and offloading for a typical DN model. The neural network is partitioned into two parts and executed on the client and server respectively. As an advantage, workload offloading supports flexible execution of a DN model via adjusting the model prediction point, and hence provides more opportunities to meet the required runtime system performance. A case of the progressive neural architecture is shown in the right part. This approach enables the DN inference to exit at a branch, leading to a reduction in model execution time. Such a design exploits the fact that different input data has different difficulty level of processing, and the inference can stop early for easy input, while still being able to produce desired output. Each inserted branch in the progressive neural architecture is a classifier consisting of a few layers, which only requires a small amount of additional memory space and compute time. Compared to the original DN model, when reaching a branch during feed-forward inference, the confidence of the classifier is measured by the entropy of the classification results at the branch. Meanwhile, if the confidence does not exceed a predefined threshold value, the DN inference terminates at the branch. Therefore, the expected model inference time depends on the characteristics of input data and the thresholds. The progressive neural architecture can adapt to dynamic input with variable input complexity by adjusting the thresholds at branches. So the transformed model constructed offline supports a wide variety of model execution policies at runtime, and hence provides flexible opportunities to meet user requirements on latency accuracy and edge energy consumption. The purpose of the reinforcement learning algorithm, which also referred to as RNL optimizer, is to provide an automated and adaptive control on model execution policy over time. The RNL optimizer uses the collected execution performance data of the historical execution policy from the edge to make near future decisions, say generating a new execution policy. So the left figure here illustrates how our IR optimizer responds to environmental changes. The coordinate indicates the average latency and energy consumption for the current execution policy. In particular, the coordinate in the bottom left quadrant corresponds to a feasible execution policy that meets user requirements, latency, and energy consumption. When bandwidth decreases, the IR optimizer may try to find a new execution strategy that has a ladder layer prediction point, thus more workload at the edge. Meanwhile, to compensate for the increase in compute demand, the new strategy may also raise the thresholds at the branches to allow more early access during task executions. This will result in systems transition from the bottom right quadrant to the bottom left quadrant, and hence the new strategy can satisfy the latency and energy constraints. Similarly, when the distribution of the input shifts to be more difficult, more workloads will be executed on the edge due to the low probability to exit at early branches. Then the IR optimizer will switch to a new execution strategy that offloads more compute workload to the cloud, and at the same time raises the thresholds at some branches to allow more early exit executions, resulting in the system's transition from upper right quadrant to the bottom left quadrant. So regarding the reward design, it is calculated based on the average task accuracy and latency and energy measured in a state interval. For the first condition, when latency and energy both meet user requirement, we aim to optimize the average task accuracy. Due to the fact that it is difficult to evaluate the actual task accuracy for real-life input, we use the index of the exit branch of the input to quantify the accuracy of the task execution. For the second condition, where both requirements are not satisfied, we penalize this incorrect outcome with a negative constant. For the last condition, when only one user requirement is satisfied, we define the reward in this situation as a function which represents the difference between the current latency energy and the user expected requirement. The detailed design can be found in our paper. So we evaluate our EdgeML system based on the settings shown here. We use NVIDIA TX2 and Nano as the edge platforms, and a PC with GTX 1070 GPU as the cloud platform. We developed EdgeML on top of TensorFlow. We choose two representative DN models, VGG16 and ResNet50 as original neural network, and select two datasets, Cyber10 and Cyber100, which are widely used for mobile vision. We use 4 metrics to evaluate the performance of EdgeML: the accuracy, latency, GPU frequency, and satisfaction rate. Note that we use GPU frequency to quantify the power of edge device, which is reasonable because there usually exists approximately linear correlations between power and frequency. The satisfaction rate represents the percentage of executions that satisfy the latency and energy constraints imposed by users. So in order to validate the effectiveness of the EdgeML, we compare the performance of EdgeML with 3 types of baselines. The first one is ablated EdgeML. Edge non-branch refers to EdgeML without an early exit mechanism, which means that no branch is added to the original model. In EdgeML T1, the threshold values at all side branches are rounded down to be the same as the first branch. Similarly, for the ablated variant EdgeML TL, the threshold values at all the side branches are rounded up to be the same as the last side branch of EdgeML. The second baseline is neurosurgeon. So to reflect the advantage of dynamically adjusting execution policy in EdgeML, we compare EdgeML with this approach that based on static workload offloading mechanism, which is one of the state-of-the-art DN offloading frameworks. The third one is MOEA. We design a baseline based on the multi-objective evolutionary algorithm to evaluate the effectiveness of IR optimizer in EdgeML. MOEA baseline adopts a non-dominated sorting genetic algorithm to replace the IR optimizer in EdgeML. For our experiments, the user bounds on latency and GPU frequency are set as 0.1 second and 1.2 GHz, respectively. So here we show the overall performance comparisons of average reward and average satisfaction rate among these baselines. We can see that EdgeML significantly outperforms.
Did you just automatically stop, or we didn't present the result?
The presentation, I mean, the video ends after 15 minutes. So, Zoe, do you want to continue after the result?
Yeah,
can
actually, I
because
think
we started a little late, can we give the presenter like 3 more minutes?
Sure.
Please go ahead. So Jiho, just share your video and just play the last segment.
actually, I can just present live.
Okay, that's fine.
So can you hear me?
Yeah, okay.
Okay. So this slide shows the average latency and GPU frequency correspondingly fall beneath the usual bounds. After 250 epochs, although these exist some cases that either latency or GPU frequency exceeds the bound, the IO optimizer can find the optimal action sets by leveraging the learned prior knowledge, leading to the rapid consistent convergence. The final satisfaction rate in this experiment is 0.35. So when deploying HML to a new edge device, a naive way is to train the IR optimizer of HML from scratch. So to speed up the deployment of HML, here we show the result of our design of transferring IR optimizer from a developed edge device to a new device. In this experiment, we first trained the IR optimizer of Jetson TX2 for 1,000.
You change your slide. We're still on slide 17.
Oh,
you put it in presentation mode.
Yes. Can you see it right now?
Yeah.
Okay. So we first trained the IO optimizer on Jackson TX2 for 1,000 epochs, and then transferred the MDP traces to the target device, which is Jetson Nano. So the first 200 epochs in the average accuracy figure suggests that our approach can adapt to the target device and achieve better performance than baseline. Note that there is a search process at the very beginning of the deployment of our method. This is because the computing power on Nano platform is substantially weaker than TX2, and thus the execution policy generated by the original IR optimizer may not be efficient on the new platform anymore. However, our method can quickly adapt to the new device compared with the baseline train from scratch during 0 to 200 epochs. So the average satisfaction rate result shown in the right figure shows that the gap between the two curves tends to saturate after convergence. So all in all, we propose HML, which combines the workload of loading mechanism and progressive neural architecture to support flexible DM model execution policy on the edge. HML represents the first framework that supports online AutoML for edge computing applications. It allows adaptive environment or network structures that can run with limited resources on edge and IoT devices. The IR-based framework can allow HML to automatically adapt to the environmental variations, such as communication channel conditions between the cloud and the edge devices, as well as dynamic input characteristics. Our experiments show that HML achieves huge performance improvement under dynamic environments. So here I'm going to end my talk. Thanks for listening.
Thanks for the presentation. Is there any questions from the audience? You can unmute your mic and ask directly, or you can post it on chat. I can relay the question. So let me start with a clarification. So in your solution, you need to do the training of RL online. So yeah. Where is the training executed? Is it on the edge device or in the cloud?
Yeah, the IR algorithm is running on the server, the cloud.
Okay, so in your evaluation, have you done any assessment of the convergence speed and the convergence time?
Yeah, actually, usually when we doing the experiments, the IO optimizer will usually converge after 400 or 500 epochs after training. So.
And how long does it typically take? Because my understanding is that before it converges, the decision It's unlikely to be optimal, right?
Actually, it depends on the initial network, I mean the DN model, because because in one epoch of the IR optimizer, it includes one or multiple epochs of the DN inference. So usually it takes like 20 to 30 minutes of training, but it depends on the data set and the DN model we are inferencing.
So basically your solution would have the warm-up time for it to be able to really execute and meet the kind of quality of service requirements, right?
Yes, that's correct.
Okay. Any question from the audience? Okay, if not, let's thank the speaker again, and we'll move on to the second paper in this session. The second paper will be presented by Xian Shuai, who is a third-year PhD student at Chinese University of Hong Kong, also supervised by Professor Guo Liangxin. His research interests are mainly in sensing and computing in IoT, especially in practical scenarios where data or computing resources are limited. Qian, please go ahead.
Okay, let me share the screen. Hello, everyone. I am Xian Shuai. This is a joint work with some collaborators and my advisor, Professor Guo Liangxin. Recent years, thanks to the breakthrough on deep learning, we have seen major progress in many computer vision tasks, including visual recognition, object detection, object tracking, and scene segmentation. These tasks are mainly based on images or videos taken from RGB cameras. A key advantage of the camera is its high resolution. However, cameras do not work well in many real-world environments, especially when the illumination condition is poor or there exists fog or smog. As a result, existing computer vision algorithms may not achieve good performance. In addition, it's a well-known issue that current vision algorithms are data-hungry, requiring tremendous data for training. To improve the accuracy, we often need to collect data from various scenarios, which is labor-intensive. One of the emerging sensing technologies that can address this issue is millimeter wave radar. They are robust to different environments, including the poor illumination and bad weather. The sensing range of radars can also go beyond 50 meters. Besides, they are getting more and more affordable. As a result, millimeter wave radar are getting increasingly popular in applications like autonomous driving, traffic monitoring, and also indoor applications, including people counting and residence occupancy sensing. But millimeter wave radars also have critical shortcomings. In particular, the output point cloud are sparse and noisy because of multipath effects and low angular resolution. As you can see from these two figures, the radar can only give the approximate location of the two targets and fail to separate them, while the object detector manages to detect the two nearby targets using the RGB camera. In summary, the sensing capabilities of radars and cameras are actually complementary to each other. Based on this observation, it's necessary to fuse them. We reviewed the existing deep learning-based approaches on radar and camera fusion. They usually follow an end-to-end training strategy, where the labeled image and radar data are directly fed into the network in pairs. This kind of approaches have two drawbacks. First, as we know, the image feature extraction requires a lot of data for training. That means we need to collect and allocate a large amount of radar and camera data, which is labor-intensive. Besides, the fusion networks are usually specifically designed. They cannot leverage state-of-the-art object detectors. For example, if we want to integrate a new image-based detector to improve the fusion performance, we may have to completely redesign the network architecture and do retraining. To this end, we propose IoTDI. Our goal is to develop a sensing system that can leverage the fusion of radar and camera to achieve the following objectives. First, it should be highly robust and accurate in real-world scenarios. Specifically, we want to achieve the same level of performance as the state-of-the-art image-based vision algorithms. And at the same time, the system should work well under challenging scenarios, like in the poor illumination conditions. Second, the system can be trained with a small amount of data, which can reduce the effort on data collection and can be easily deployed. Third, the system should be compute efficient and can run in real time on embedded devices. In order to achieve these objectives, IoTDI has two key features. One of the features is a decoupled training strategy. In particular, we first train image-related layers on large public image datasets, like ImageNet or Microsoft Coco. Then, we train other layers on customized small image and radar datasets. The advantage is that it can fully utilize the large image datasets for extensive training. Other layers that are not directly exposed to image features are usually more scenario agnostic, thus can be trained with only a small amount of fusion data. Another key feature of IoTDI is that it uses a two-stage object detection architecture. We can see here, the first stage is performed once for every frame, where radar and camera generate their own bounding boxes individually. Of course, there may exist some false positive boxes that should be eliminated. The second stage is called the box refinement, which is needed only once for every box. It does two things: adjust the box location and determine whether each box should be kept or discarded. In this example, the rightmost red box is deleted during the refinement. This two-stage architecture allows IoTDI to leverage the state-of-the-art object detectors, because in the first stage, we let the object detector generate its own bounding box proposals. As a result, we can replace the image-based object detector independent of other components. Meanwhile, previous literature shows that a two-stage structure can improve the accuracy. Here comes to the overview of IoTDI. It mainly includes 4 modules: image-based object detector, radar branch, ROI cropping, and ROI-wise refinement head. As shown in this figure, both the image object detector and radar branch will generate feature maps and bounding boxes. The combined feature map from two modalities are cropped by the box proposals from two modalities. Finally, every cropped feature map will enter the refinement module. We will introduce them one by one in the following. The object detector takes the image as inputs. The image first are sent into the backbone neural network for feature extraction. Then, a detection head is used to generate the final bounding boxes. Both the internal feature maps and the final result are utilized later. It's worth noting that most object detectors, including ULO and SSD, follows this structure. That means our system is highly compatible to current object detectors and can continue to take advantage of the progress in detection models. Similar to the image-based object detector, the output of the radar branch also includes feature maps and 2D bounding boxes. In order to handle the unstructured point cloud data, we first map the point cloud from 3D to 2D coordinates and calculate a 3-channel heat map consisting of information of the point cloud about the density, depth, and the mean velocity. Then this heat map is sent to a 3-layer CNN for feature extraction. Regarding the 2D bounding box generation, we first cluster the point cloud using dbScan. For every cluster, an approximate 3D box can be estimated. Unfortunately, some noise are also clustered as boxes. To delete these false positive boxes, which flickers among frames, we utilize the temporal information. Specifically, we perform box association between adjacent frames and apply a Kalman filter. After these steps, we obtain 3D bounding boxes, which are subsequently projected into 2D. After getting the feature maps and the bounding boxes, from both modalities, the next step is ROI cropping. It crops the big global feature map according to the position and generates a small 7x7 feature maps for every ROI. Those small feature maps contain local information and will be sent into the ROI-wise refinement module for further processing. The ROI-wise refinement module does two things: adjust the box position and determine whether to keep or discard the box. To adjust the box position of every box, a region CNN subnet is applied here. It also acts as a middle module to provide local image features for the Fusion module and the Ensemble module. The Fusion module fuses the local image features and the local radar features. It can comprehensively consider likelihood that whether the box includes a positive sample by adding the confidence scores from two modalities and applying a sigmoid function on it. Finally, the Ensemble module in turn uses the result from the image-based object detector. It acts like a double insurance of the multimodality fusion. It will output the final decision to keep or discard the ROI. In our implementation, the training includes 3 stages. The first and the second stage train all image-related layers, including image-based object detector and the RCNN module. They are trained on large public image datasets like Coco and Xdark. The third stage trains all other modules on customized radar and camera datasets, which is relatively in small scale. We build a testbed by integrating a camera and an off-the-shelf radar on a fixed platform, which is shown here. Our collected dataset has around 1,300 frames. We use our dataset in a 5-fold manner, where 4 folds are used for training and the remaining 1 fold is used for testing, and this process is repeated for 5 times. Here are 2 example images of our dataset. Our collected data includes both ordinary light conditions and low light conditions, and includes 7 different places. Alright, we are now ready to talk about the evaluation. For metrics, we adopt IOU, the intersection of a union, to determine whether the detected box is true or false. If the IOU between the detected box and the ground truth is larger than a threshold theta, the box is regarded as a correct one, also called the true positive, otherwise the false positive. If we fail to detect the target, we note it as a false negative. Based on them, we can further calculate the recall and the precision. Recall is a true positive over a true positive plus false negative. Precision is a true positive over the true positive plus false positive. Finally, we got the mean average precision, which called MAP in short, a widely used evaluation metric in object detection. MAP is equal to the area under the precision recall curve. Higher the MAP, more accurate the detection result will be. For baselines, we adopt naive diffusion, which has been introduced in previous slides. It follows an end-to-end training strategy. Also, we compare our method with image-only object detection approach, the tiny YOLO V3. We report the results under different illuminations and different confidence threshold. Okay, in ordinary light, MIDI-I achieves slightly better performance than YOLO, while in low light conditions, the improvement is more prominent with the help of radar. An interesting result is that the naive diffusion approach performs very badly. This is because that our customized dataset is not in large scale, so layers that handle the image feature extraction cannot be trained well, as these layers are very data hungry. We also conduct experiments when using SSD as the object detector, and we achieve similar results. We will skip the details here, which can be found in our paper. Now, we are going to see how 2 sensors respond to different environments. In ordinary light, camera is expected to dominate the detection, while the radar should be playing a supporting role. In low light condition, radar should become more important. Our experiments exactly confirm this expectation. In particular, for positive samples, the confidence scores from the radar keep stable, regardless of the light conditions, while the confidence scores from the camera decrease a lot from the ordinary light to low light condition. Both radars and cameras are good at suppressing the negative samples, which is good. We also test the robustness of our system by putting it in very challenging dark scenarios. We find that MIDI-I outperforms the ULO by a large margin under different confidence thresholds. In this example, the white boxes are ground truth boxes, and the yellow ones are detected boxes. We can see they are very close to each other. Okay, let's see a demo video. 3 approaches from left to right are radar only, camera only, and fusion approach. We can see clearly, radar tracks a person from frame to frame. However, the box location is not that accurate. Image-based object detector can detect the accurate position of the target when the person is in bright area, while it fails when the person is in the shadow. Our proposed MIDI-I take advantages of the strengths of the 2 sensors and can detect the target very accurately. We believe our technology has potential application values in many scenarios. For example, in smart home, our system enables continuously person tracking and counting in challenging scenarios. In smart factory, it can be installed on robots to avoid the unconscious person in its path. In intelligent transportation, many smart lampposts have already equipped with cameras and radars. Our technology can help them to track vehicles and people in all weather conditions. When mounted on vehicles, this technology can also allow autonomous vehicles to prevent collision more reliably using only radar and camera. In conclusion, we propose MIDI-I. It achieves highly robust system performance under different environments and is compatible to different object detectors and is also compute efficient. Last but not least, it can work with small radar and camera training data. Hello, everyone.
Thanks for the presentation. Is there any question from the audience?
Yeah, it's the end of the presentation.
So for your work, you use the confidence score from the different branches, the radar and the camera branches, as a way to fuse a decision. So that confidence score, is this the output of the, so how is the confidence score computed?
From the radar branch. Okay, can I reshare the screen and go back to that slide?
You're sharing your screen still.
Yeah, I want to share the screen and to go back to that slide.
No.
Okay, let me share the screen. Maybe I can't share. I don't have the authority to share a screen now.
We actually see your screen.
Okay, thanks. So the radar and the camera.
Can you share again?
Oh, okay. So the radar and the camera here, the confidence score from the radar is generated by CNN. and enter into the fusion module. And the confidence score from the camera is generated by the RCN subnet. So they are fused by this fusion module. This fusion module adds the confidence score from two modalities together. Right. So the confidence score basically describes how likely there exists an object.
So that's just like the softmax output, right?
Yeah.
Okay.
Exactly.
There are two questions from the audience. The first one is that the latency is higher in your proposed network compared to baseline. Do you have any plans to improve the latency?
Yeah, we will have conduct some experiment on it, but due to time limits, we skipped in our presentation. So generally speaking, the extra latency brought by MIDI is 1 order of magnitude smaller than the latency, than the overhead of tiny YOLO V3, right?
Okay. In the interest of time, we'll move on to the third paper. So the third paper is going to be presented by Max Schaufel. Max is currently a PhD student in electrical engineering at University of Kaiserslautern in Germany. And he received his Master of Science degree in 2019, and he's currently working on efficient implementation and hardware acceleration of post-quantum safe cryptographic algorithms on low power applications.
Yeah, so good evening from Germany. Can you hear me?
Yes.
Okay. Thanks for the introduction. I'm going to talk about the application of a new type of cryptography, of post-quantum cryptography, to low-power secure IoT infrastructure. So let's start with the motivation. The motivation basically starts with quantum computers. In general, quantum computers have many beneficial applications. For example, they might yield very good results in medicine in future or in material science. However, they also place a very serious threat on state-of-the-art cryptography and therefore security. And as many of us know, we already have very critical problems with security in the IoT area because we often have limited computational power, and our device might also be energy constrained because it is battery powered. Now, how to solve this problem? The first part of the solution is based on a standardization process, which is currently conducted by the US NIST, which desires to find new cryptographic algorithms that are called post-quantum cryptography, which are simply resistant against those attacks by quantum computers. The second part, and this is the big question here, are perhaps hardware accelerators for exactly those post-quantum cryptographic algorithms. The thing is that there are already many papers published which developed such hardware accelerators, but we realized that there is no real case study in a low power application which just checks how many acceleration is necessary to get good results in a typical low power environment. This is what we wanted to address in this work. So why are we even bothering with PQC in IoT? I think all of you are familiar with IoT. Today, it is the case that industrial secrets and also critical infrastructure are inside of IoT, and their security or the security of their communication is based on TLS, on a cryptographic protocol. And TLS uses a public key cryptography inside it, which bases on either the hardness of large integer factorization in case of RSA, or on the hardness of discrete logarithms. Now, due to the recent advancements we had in building quantum computers, Google achieved a quantum supremacy in last year. It is estimated that quantum computers can break those public key crypto systems latest by the end of this decade using Shor's algorithm in polynomial time. Now, what does it mean if this cryptography is broken? First of all, TLS uses a combination of symmetric crypto and public key crypto to establish a secure connection. And the symmetric crypto itself is not directly threatened or only minor threatened by the quantum computer because it uses a different hardness assumption than public key crypto. Public key crypto is used to first establish authenticity during the connection by using digital signatures. And second, to protect the communication against eavesdroppers by using key exchanges. Now, the attack scenarios are a bit different for quantum computers onto those two crypto systems. For a successful attack on a digital signature, the attacker needs already access to a quantum computer. This is completely different for key exchanges because there's the so-called store now, decrypt later scenario. And the key idea of this scenario is to start harvesting data already today, which is encrypted, which cannot be read today, but speculate that the attacker will be able to decrypt this communication in future with the quantum computer. For some applications, this might not be critical, but for governmental applications or for applications where we have very important industrial secrets, this is critical. Therefore, we did not consider digital signatures in this work, but we focused on post-quantum key encapsulation mechanisms, which are used to provide a post-quantum secure key exchange. Okay, the standard library which is used in embedded devices for TLS is embeddTLS. I guess some of you may know it. And we used the source code of embeddTLS and built a custom extension of this library to allow the integration of this new public key algorithms of the post-quantum camps. And we made sure that we did not change the protocol itself, so it is still the original TLS 1.2 protocol. And we realized that the major challenge in this implementation is the memory footprint on embedded devices. How does such a key exchange work? Well, the aim of the key exchange is always that client and server agree on the same shared secret at the end of this key exchange, which is then used for actual application data encryption. First, the server creates a key pair, a public key and a secret key. Here, the green parts are public known, the red parts are secret. The server transmits the public key to the client. The client takes this public key and calculates a shared secret and a ciphertext. With the encapes function, then the client sends the ciphertext again back to the server, and the server uses this ciphertext to get the same shared secret as the client, sorry. So even if an attacker would interfere here, he could not perform the decaps operation to get the same shared secret because he would not have access to this secret key. Now, in this NIST process, I mentioned a lot of different problem families. I just told you that for the classical cryptography, the problem families rely either on the hardness of large integer factorization or on the hardness of discrete logarithms. For the new post-quantum camps are basically three problems, either lattice-based, which means hard problems over lattices, for example, finding the shortest vector in a lattice, problems in coding theory, or problems in isogenies. All those algorithms which have been proposed there differ in key sizes, they have different performances and different levels of trust in their security. And this process just advanced to the most likely last round in last July. And there they selected basically finalists, which are Andrew, Kyber, and Saber. And those finalists are very likely to be standardized in future. Nonetheless, as those are still quite new problems, and we cannot completely tell if those problems are really secure, even against classical computers, it is a good practice to observe different hardness assumptions just in case that one turns out to be insecure in future. That way, it is possible to create a crypto agile system, which means that we can fast switch between different cryptographic systems. Okay, we used quite a standard IoT setup for our implementation here. We have edge devices, which have as a microcontrolling unit a typical ARM Cortex M4. We have some transparent gateway and we have some server. There are some different versions of TLS, for example, DTLS, but in that case, we would have to execute some re-encryption on the gateway, and therefore we would provide another room for a further attack, and we wanted to avoid this. Therefore, we have a complete end-to-end encryption here from the edge device to the server. We have a typical protocol stack, which means Bluetooth Low Energy, IPv6, TCP, TLS, and MQTT. And the cryptography was basically inserted here in the TLS stack. Okay, let's get to the measurement results. We measured the latency of one TLS handshake, of multiple TLS handshakes, always on the client side because we want to focus on the low power side, and then compared it with the state-of-the-art cryptography. Here on the left side in this graph, you can see ECDHE. This is basically the state-of-the-art. And the other remaining algorithms here are all post-quantum camps. So they are supposed to be secure against quantum computers. We can see 3 different bars in this figure. One bar is NCAPS. This is basically the most interesting part for us because this is the calculation which is executed on our edge device. We can see the time which is necessary to send the ciphertext, the CT I just showed you, and just the further handshake steps which are required during this TLS handshake. Now there are 3 important observations from this graph. First thing we see here is that basically post-quantum camps do not have such a large overhead compared to conventional state-of-the-art cryptography. It's about 10% in time in our setup, so it's still reasonable. Second, more important one is we cannot even see here the share of NCAPS, so of the cryptographic calculation on this bar and this bar. So all those Kyber, Lightsaber, Andrew, and so on, those are the structured lattice-based camps, the finalists from the NIST process, have already very efficient calculations without any hardware accelerator. This means that it is very questionable if there would even be benefits of dedicated hardware accelerators, which are currently heavily developed. The third thing we see here is that not the calculation, but the additional bandwidth, which means the larger ciphertext and larger key sizes are the main contributor to this TLS handshake overhead, which we have here in the post-quantum camps. There's one exception from this, which is SIG. This SIG has a very large orange bar, which means very intensive calculations. So here a hardware accelerator might be a good idea. Just to make this point even more clear, how important the public key and the ciphertext size is. Here on the right side, you can see again the same picture as before. Left side, we see the bandwidth requirements of the key encapsulation mechanisms, which is basically the sum of ciphertext in blue and public key size. And what we can see when we compare those two graphs is that the trend lines between the different algorithms here in terms of bandwidth requirements and in terms of handshakes latency is basically the same. So in other words, this is the clear proof that this new post-quantum camps are mostly data-driven in our application, the overhead. It's not driven by computation, but by data exchange. As we are in a low power environment, we also obviously wanted to know how much energy those post-quantum camps cost us. Therefore, we did some theoretical battery runtime estimations where we used a standard lithium AA cell and assumed that we just have 70% of the stored energy usable just to compensate things like aging effects. Now we measured the energy of one complete TLS secured MQTT transaction with 12 bytes of application data. But we did not include any energy for data acquisition because this is strongly dependent on the used sensor. What we can see is that we get very long battery runtimes even for quite a lot data transfers by day. For example, if we use the struct level 1, which corresponds to the SLB camps, to the structured lattice space camps, we get roughly a battery runtime of 10 years if we transfer data 700 times per day. We know that this is really artificial a bit, but I think it is safe to say that secure communication is not really a problem in this case. Okay, let's come to the conclusion. First, dedicated accelerators seem not to be necessary to use post-quantum camps in low power environments. Second, we can use all three problem families, so isogeny, code-based, and structured lattice-based camps to reach years of battery runtime. And most importantly, the latency overhead of post-quantum camps is determined by larger bandwidth requirements and not by computation. To summary, I think this is a very positive result. We can say that post-quantum camps seem already feasible today for low power IoT with state-of-the-art hardware. So there are no changes required on the hardware side. Thanks for listening.
Thank you for the presentation. Any questions from the audience? So I read like the beginning of your bio said that your interest is in efficient implementation of hardware acceleration for post-quantum.
Yeah.
So is this a negative result to you, although it's a positive result to the community?
Yeah, this is a very good question. I think there are also other applications where we do not use such, let's say, not really latency optimized networks where we still need hardware accelerators, especially if we use not the structured lattice-based camps, but Psych, for example, or one of the code-based camps.
Okay, you mean the ones that have bigger orange bars?
Yeah, exactly. The one with the big orange bar, for example. And yeah, but to be honest, it was a really surprising result for us because we saw that there were a lot of papers designing hardware accelerators, and then we did this measurement and realized, oh, it does not really make always sense. Let's say it like this.
Yeah, interesting. Another question is, so I noticed you talking about the data requirements are different for different post-quantum cryptos. I'm not familiar with the differences, but it looks like the key sizes are different. Is it fair to make the comparison if they have different key sizes, which I would assume that imply they have different in terms of their cryptography properties are somewhat different?
Yeah, I got the question. Note that the key sizes in byte does not necessarily track back to their real security. So there are some defined security levels which say, okay, we need 2 to the power of 128 operations to break this crypto system. And depending on how the CAM is designed, you need larger or smaller keys to reach this defined level of security.
Okay, so the ones that you compare have the same security level.
Yeah, exactly.
Okay,
but not the same trust level necessarily. Because some say, okay, there might be some space for an attack if you design the cam like you did there.
Understand. Is there any questions for the presenter? Okay, so if not, this actually concludes our session. I'd like to thank again all the presenters and also the audience for attending.
Thanks.
Thank you all. After this session, there is a break for 15 minutes. And at 2:15 p.m., you can visit the virtual reception by going to Getter Town as you visit for the poster session. I just click the link. I give you the link. You can visit this link to go to read and how you can access the Getter Town for virtual reception. Okay?
Okay, thank you.
Thank you.
Bye, everyone.
Bye.
Bye.